Okay, well, welcome back. Session three. Last time we were together, we talked about a lot of fundamental stuff. We talked about basically the science of electronics. Today, what we want to do is to get into some actual circuit stuff. So the fundamental law of circuits is called Ohm's law. Today, we'll discuss Ohm's law. And also, we'll discuss two other quantities that have to do with electronics. We'll discuss power, and we'll discuss energy, and we'll calculate cost of energy. Before I get started, a couple of things. We will meet for our first lab a week from today. So next session, there will be no recording. We'll actually come in and you'll have a lab. You actually have a couple labs, and you want to make sure, hopefully by now you have your digital multimeter. There was no way for you to do lab one without the digital multimeter, so I'm assuming that you have it. You want to make sure you bring the digital multimeter. You will not need your analog digital trainer next week. The circuit we're gonna deal with, we don't really deal with that until maybe the week after next week, or actually 2 weeks after next week. So you don't have to bring the digital analog trainer. I will have some breadboards for you to build your circuits up on. So, but bring your digital multimeter. You will need that. As far as work to hand in, I think the only thing I had you upload was maybe the universe assignment. Whatever's uploadable is already there. I know the labs were uploadable, the energy assignment, the homework, and then there's a supplementary quiz. There's a homework one. Those assignments you'll bring in next week when you meet for lab. So what I want to tell you is to make sure you watch the Blackboard announcements, and I'll have things to say about how that session is going to look next week. So anybody have any questions for me before we start? Any general questions? Okay, well, we have to turn, the professors here have to turn the attendance in by the 4th. So if you haven't sent a text, make sure you text this number, EET 131, first and last name. If you don't do that, we don't turn the attendance in, then in the school's eyes, you're not here, and then you get removed from the class. I think they charge you for it. So make sure you've been sending texts. If not, here's your last chance to get on the roster, the official roster. Send me a text to 513-494-6162. EET 131, your section is 200, and you want to put your first and last name in that text. All right, so somebody asked about the analog kits. Where do you buy it? The bookstore has them, but you probably get a better deal on Amazon or online. So I think the bookstore, I don't know, they might be like $200 or something like that. But did anybody buy their kit yet? Their trainer? Anybody buy their trainer?
Yeah,
I bought it. When it shows up, I don't know.
Oh, you ordered it? Oh, you ordered it online? Okay.
Yep.
You know, that's been an issue though. I ordered and actually paid for some. I rehab houses on the side, and I ordered some pipes and some stuff for to do some plumbing, and it was supposed to arrive on, I believe, it was supposed to arrive on the 3rd, which is tomorrow. But they just sent it out today, so it won't arrive by then. And then there's just been issues with deliveries, U.S. Postal Service and UPS, and probably all the delivery companies. I don't know. But yeah, look online, and I don't know. Normally, I say a good price. Students in the past have gotten that for around about $150. I don't know what the bookstore charges for it. I think it's north of $200 is what they asked for it. But you guys can get it. You know, if you don't have it right now, it's not a big deal. We have all the equipment in here you need to do the labs. The main thing, the main reason you want to get that trainer is if we end up going virtual again and not doing no face-to-face, you have to have the capability to do circuits at home. So that's good for that. And then if your major is EET, you'll actually use that in other classes. So you want to learn how to use it in this class. So, but you can ask about that later. I want to go ahead and get started. Now, I want to, before we get into the lecture for this week, let's review 3 concepts we talked about in the last class. We talked about the concept of voltage. We talked about current. We talked about resistance. And we didn't go into the physics of resistance yet because when you come in, one of the things you'll do, one of the labs you'll do next week deals with resistance. So I didn't go into the details of resistance, as much detail as we went in on voltage and current, because I knew we were going to do a lab on resistance. So you'll get more of that next week. But let's just talk about these 3 concepts. When we had our discussion last week, based on that discussion, how would you describe or define voltage? What is voltage? Anybody? What is voltage?
Voltage is electrical potential.
Okay. So voltage is electrical potential. And what does that mean? Well, there's 2 kinds of potential. Well, there's actually more than 2. But there's 2 main kinds of potential that people think about. When I say people, I mean scientists. You can have a gravitational potential. And when I say potential, I mean potential difference. It's always a difference between 2 points. An example of a gravitational potential is I have a mass. My hand is a mass. This object is a mass. If I do work to separate the object from my hand, so that I have an electrical potential difference, I have a gravitational potential difference between this point and this point. So I have potential energy stored because this thing has position above ground. I can separate charge and have exactly the same thing, but if I separate charge, I don't have a gravitational potential difference. I have a electrical potential difference, or voltage. So said another way, voltage is nothing more than the separation of charge. Voltage is the separation of charge. Anything that creates voltage, batteries, generators, solar cells, anything that creates or generates a voltage, what that thing is doing is separating charge to make an electrical potential difference. So voltage is the separation of charge. We use the letter V, capital V, as the symbol for voltage, and the unit for voltage. If you did the supplementary quiz already, you know the unit is a joule per coulomb, but 1 joule per coulomb, we call that a volt. So the volt is a unit for voltage, and that is also capital V. It's one of the symbols that has a V for the symbol and a V for the unit. Okay, so voltage is a separation of charge. How would you define or describe current? What is current?
The
Charge
flow of
in motion.
electrons.
Current is charge in motion. Current is charge in motion. And I heard somebody say current is the flow of electrons. So that's exactly right. So current is charge in motion. Well, you're going to learn today that if I have something that's not moving, charge. If I have something that's not moving and I want to make it move, what I have to do is apply a force. Well, how do I apply a force? You apply a force by taking that charge that's free to move and placing it in a potential difference or voltage, and that voltage can cause a force, an action at a distance force, to act on that charge and move that charge. And once that charge is moving, it has kinetic energy, and anything that has kinetic energy can do work. It can do physical work, if I'm talking about physical things like this. It can do electrical work, if I'm talking about charge moving. It can do electrical work like lighting up a light bulb, turn your cell phone on, turn the TV on, whatever that circuit's designed to do. So, specifically speaking, current is the flow of electrons, or you can just kind of say in general, current is the flow of charge. And you want to make sure you understand it takes a voltage to make a current. The cause of a current is a voltage. Voltage provides the pressure or force to make the electrons move. What is resistance? How would you describe or define resistance?
The property of matter to slow down current, I suppose.
Okay, good choice of words. So resistance, I'll describe it next week when we go into detail of resistance. But I'll describe it as electrical friction, and that's kind of nice because friction is the force that opposes motion. Resistance is the quantity that opposes the flow of current. And just like friction produces heat, resistance always produces heat. So the analogy between resistance and friction is a good one. So we use the symbol V for current. We use the symbol V for voltage. For current, we're going to use the letter I, capital I, to represent the current. And the unit for current would be the coulomb per second. But what we said in the last class is that if I have 1 coulomb per second, that's equal to 1 ampere, or amp for short. So the unit for current is capital A, for amps or ampere, and the symbol we use is a capital I. And then resistance, the symbol for resistance is a capital R, and for the unit for resistance, we use this omega. This is the Greek letter omega. It looks like a horseshoe. So we use that. Or sometimes we actually just spell out the word. You'll see ohm. So you might see a resistor that's 15 ohms. You might see 15, and then the omega for ohm, 15 ohms. Or you might see 15, and they'll actually write it out ohm like that. So either way, it's okay with me. Probably this one is the easiest and fastest to write. So these are, we talked about a whole lot of stuff in the last class, a bunch of stuff. So if you missed the last class or you need to review the concepts, there's a past lecture, I think it says past videos or past lectures or something up on Blackboard. You'll find the videos there. So go back, rewatch that, and review that material. And there's one thing I did not talk about that I want to talk about, at least I don't think I talked about it last week, that have to do with these quantities that I just described for you tonight. In electrical engineering, there are graphic symbols that we use to represent these quantities. All these quantities are very abstract. I mean, you can't touch a voltage. You can feel a volt. Well, you don't really feel a voltage, you feel a current. So you can imagine electricity. All this is kind of abstract. So we like to have these symbols that we can draw so we can think about these in a certain way, or we can describe them pictorially. And so I'm going to show you 3 ways to represent voltage or a voltage source. I'm going to show you one way to actually 2 ways to represent current. I'm going to show you how we represent resistance. And then next week, we'll go into detail of resistance, or actually a whole different spins that we can take on resistance, but we'll get into the details of that next week. So these are symbols. So write this down. These are the graphic symbols that we use to represent voltage, current, and resistance. So for voltage, I can use one of 3 symbols. I can use this symbol. I can use this symbol. And when you use one of these 2 symbols, I have a long line and I have a short line. Long line and a short line. The long line is a positive polarity. The short line represents the negative polarity. And over here, long line, positive, short line, negative. So when you deal with voltage, then you have this concept of polarity, plus and minus. You're probably familiar with that. If you ever jumped a car battery, you know one terminal on the battery is positive, where they're talking about this. And the other terminal is negative, they're talking about this. And often when they use this idea of polarity, for lay people, they color code it. They use the color red to represent a positive polarity, and they tend to use the color black to represent a negative polarity. So you probably are familiar with that from somewhere. So these are two ways you can represent a voltage or voltage source. By voltage source, I mean any device that produces voltage, any device that separates charge. The first one over here on the left is a cell. And the one here is a battery. So people get this wrong a lot. They call this a battery and this a battery. They're not the same. This is a cell and this is a battery. Having said that, you can use either one. I mean, I don't care which one you use. If you want to call a cell a battery and a battery a cell, you can do that in here. But when you walk outside that door, I want you to know what you're talking about. So I'm not going to go into it today. I think this is the topic of next week. But strictly speaking, there's a difference between the cell and the battery. Among friends, you can treat them as if they were the same. when you go get your job at GE, Procter & Gamble, wherever you're going to make all this money when you graduate from here, make sure you know the difference between a cell and a battery. And we'll talk about that next week. The third way of representing a voltage source is just a circle, and you show your polarities like this. And then what you do is you write the magnitude of the voltage next to any one of these symbols. So if I'm talking about a car battery, well, car battery is 12 volts. So I might draw the battery, put my polarity sign there, and I'll put the 12 like that. That will represent a 12-volt battery or voltage source. So write this down. Be familiar with those. I think you had a quiz where you told me quiz 1, you kind of told me what grade you expect to get in the course. But I don't think you had any real quizzes where you had to calculate and reproduce some of the information I gave you in class. So on that quiz, when you have it, I may ask about something like this. So make sure you're able to recall that I can use any one of these symbols right here to represent a voltage source or a voltage in general. Current. Let me talk about current. To represent current, we simply use an arrow. An arrow. So I just show the arrow, and I put the letter I over here, and then usually you write the magnitude of the current above the arrow. So if I have a 3 amp current flowing, I'll just write 3 amps above the arrow. Now I have a few other things I want to talk about in regards to current, but I'm going to wait until I get to resistance, and we put everything together, and I can talk about, there's 2 different kind of currents I want to talk about, and then we'll get into the lecture for tonight. Now for resistance, there's actually several ways you can represent resistance, but the general form of a opposition to current flow, any kind of opposition, it looks like this. It looks like a saw, the bottom of a saw. So that's a symbol for resistance or a device called a resistor. If I want to represent resistance, then I use this symbol. Typically, you write the magnitude of the resistor by the symbol. So it's 1500 ohms. I write 1500 ohms. So I can spell out the word ohm. So you want to make sure you know each of these symbols, and as we go through the course, you'll pick up more of these symbols that we'll talk about. And if you go through part 2 of the course, which is AC circuits, this is DC circuits. Next course you'll take is AC circuits. Then you'll get even more of these symbols, and before you know it, you'll be able to put together a whole electrical diagram. When you put these together into like a road map for a circuit, we call that road map a schematic, and you'll basically learn how to build schematics as you go through these courses. Now, here's what I can do with these symbols if I wanted to. I can actually take the symbols and maybe I have a voltage source, and a resistor. And what I can do is I can draw wires to connect the voltage source to the resistor. So when I do that, I connect this to here and this to here. Now current can actually flow through this circuit. This is called an electrical circuit. A circuit is a closed path through which current can flow. And so what happens is current, and just to revisit a concept from last week. From last week, we talked about voltage being a separation of charge. So let's say I have charge. I got positive charge here. Now here I got negative charge. This is my electrical potential difference. I take charge and I separate it, and then I have an electrical potential difference or voltage. If you do that, then in the area between this charge, there is a field. A field. And that field is called the electric field. It's important to talk about fields because if I put an electron right here, now these charges are fixed. They can't move. I use a battery or generator to separate these charges. They're not free to move. I separate the charge, and in between this region of separated charge, there's this field, an electric field. Just like if I have two magnets stuck together, if I pull the magnets apart, then between those two magnets, there's a magnetic field. I know there is because if I put a paper clip between them, it'll go one way or the other to stick to the magnet. Well, how does the force get from the paper clip to the magnet, or the magnet to the paper clip? It gets from the paper clip to the magnet, it travels through the magnetic field. Well, the force to make this electron move actually travels through the electric field. The electric field is the way that we can transfer energy or transfer force. It's the mechanism that we can transfer energy or force through free space. And I don't know if I mentioned the fact there's three kind of fields. There's the one you're used to, the magnetic field. There's the gravitational field that you experience all the time, even though you don't think about it. And then there's the electric field. And all these fields can carry forces. If I hold up a rock, the rock feels real heavy because it has weight. What do you mean by weight? When you say weight, what you're really talking about is the Earth's gravitational field is pulling down on this rock. So you feel something you call weight, but what you really feel is the Earth pulling on the rock. Well, how does the Earth reach up and apply force to the rock? It does so because or through the gravitational field. Fields allow forces to travel through free space. And so I can have exactly the same thing here. I can have a force travel and actually move the electron. And you know these charges are negative. Like charges repel. These charges are positive. Unlike charges attract. So this electron is going to want to move like this. And once that electron moves like that, I have current flow. I have electron flow. Now the reason I'm showing that is because if you look at the physics of the situation, current flows from negative to positive. It flows opposite the electric field. Well, if I draw that over here, my current's actually going to flow like this, from negative to the positive. So that kind of current is called electron flow. And that's the actual path that the current takes as it moves around the circuit. It goes from the negative terminal of the battery to the positive terminal of the battery. Now, the reason I'm mentioning this is because there's another way we like to think about current. I don't know if you have your book handy, but if you got your book handy, if you look at the title of your book, the front cover, it'll say Fundamentals of Electronics, but in small print under the title, it says conventional flow or conventional current version. There's two versions of this book you can buy. You can buy conventional current version or electron flow version. And most books in electrical engineering or electronics are that way. You can buy electron flow versions or conventional current versions. And what is conventional current? Well, conventional current is like electron flow in reverse. Instead of having current flowing from negative to positive, we assume that current's flowing this way. That's called conventional current flow. Conventional current doesn't really exist. It's made up. Electron flow is the actual way the electrons flow in a circuit from negative to positive. Now you might say, okay, well then why do we have conventional current flow? Well, the problem is this. The problem is when Benjamin Franklin decided that the proton would have positive charge and the electron would have negative charge. When he assigned those charges to those two subatomic particles, it really kind of caused a problem in physics. Because if you look at this, often when they talk about the energy something has, this has more energy than something down here. So we say this energy is more positive than this. So if you look at this, it looks like I have something from a negative potential to a positive potential. That's kind of like water flowing uphill. Water actually flows from a positive potential to a less positive potential or a negative potential. So I think of these as this is a potential difference. So at this point, the positive is a higher point potential than this point, then water will flow downhill. But the way we have it now with electron flow, looks like water's flowing uphill. You've never seen that before. So we got a choice. We can change the electron to be positive and the proton to be negative, then our current will flow the right way in our pictures. And it'll agree with the rest of physics, or we can just make up this current called conventional current flow. We know electrons really flow like this, from negative to positive, but when we talk about it, we're going to think about flowing the other way, and that's called conventional current flow. So do I care which one you use? The answer is no, I don't care what you use. I'm using conventional current. You always see me draw current coming out of the positive terminal and flowing to the negative terminal like that. My background is in physics, and so I think in terms of potential, and that makes sense to me from a physics point of view. But you can do whatever you want to do. The only rule I have is whichever one you choose, be consistent throughout all your work. If you're going to use conventional current flow, use it all the time. If you're going to use electron flow, use it all the time. You will not confuse me at all. But pick one and then stick with it. All right, so questions or comments on what I have said so far? Any questions or comments? Okay, well, let's get into the topic for tonight. Now, there is a topic sheet, and it will be handy if you either have that available on your screen or you print it out. I do have the capability to share documents with you through your Blackboard, so I'll put this up on your Blackboard, and you can see it. Most of these topic sheets will have practice problems on the bottom of them, so that's why it's kind of handy. If you have it right there, you can read it, because I'll put it on the screen so you can read it and work on it, but eventually I'll take it away so you can see me work the problem on the board. But if you have it in front of you, you can look at it all the time. So anytime you can print these out before class, then it'll be useful. But if you don't have that capability, I'll share this with you through the Blackboard. So I want to, on the topic sheet, we're going to talk about Ohm's law, we'll talk about energy and power, and then we'll talk about something called efficiency. And then by the end of the day, you need to know exactly what I mean when I talk about Ohm's law, what it is, what the relationship is. You need to know exactly what I mean by energy and power, the difference between the two, and we'll talk about efficiency. And there'll be some other things along the way, some other terms and concepts that you may or may not have heard before, but that you'll be responsible for. So let's talk about Ohm's law. So this is our third week of class, and we haven't done any electrical stuff. The first week was all fundamentals. We talked about scientific notation, engineering notation, accuracy, precision, that kind of stuff. That's all fundamental stuff. Last week was all physics. It was just what the rest of the semester is going to be based on. Here's what this electrical stuff is based on. Tonight, we actually start electronics. And the way we started is with the fundamental law of electronics, which is called Ohm's law. So let me talk about Ohm's law. So borrowing one more concept from physics. In physics, just kind of in general, effect equals cause over opposition. In physics, effect equals cause over opposition. So one example of that being used in physics is, let's say that the effect you want to establish is an acceleration. Does anybody know the cause of an acceleration? Acceleration means that you got something that's going to move faster and faster and faster. It keeps on speeding up. What is the cause of acceleration?
Force.
Force. And the opposition to force is called inertia, and the way we measure inertia is through something called mass. Mass. And so from this, if I use letters to represent this, for acceleration we use a lowercase a. For force we use an uppercase F. For mass we use a lowercase m. And you might recognize this as one of Newton's laws, F equals ma if you have physics. But it started right here. When Newton came up with this is what he was thinking about. But we can do the same thing in electrical engineering. Only the effect we're trying to establish is not an acceleration. What are we trying to make happen in electronics? What do we want to make happen?
The flow of current.
We want the flow of current. What is the cause of current flow?
Voltage.
Voltage. I said that at the beginning of class. It takes a voltage to make a current. Voltage is the electrical pressure to make those charges move if it's static electricity we're dealing with. So it takes voltage. And anytime I have something moving, it's always something to oppose the motion. If it's an actual object that's moving, then the thing that opposes that is friction. Friction is the force that opposes motion. When I'm talking about current, electrical current, it's not friction, it is the electrical equivalent of friction, which is
resistance.
resistance. And so engineers and scientists don't like writing out stuff like this. Number one, we're not very good spellers. Number two, it takes too long. So what we're going to do is use symbols to represent these words, but this is the relationship. So for current, we said we're going to use a capital I. For voltage, we're going to use a capital V. And for resistance, we're going to use a capital R. And this is the way we express Ohm's law. So Ohm's law the standard way of representing Ohm's law is like this, because I have cause here, I have effect over here, I have the opposition here. So I want to make sure I remember Ohm's law in that form. But you should also be able to solve for any of the three variables in this equation. So I is V over R, V equals I times R, and R equals V over I. Now, has anybody ever seen, well, tell me the difference between this and this. What's the difference between this symbol and that symbol? What does that mean mathematically? What does the top one mean?
A equals B.
Okay, what does that mean? If you say something is equal to something else, what does that mean?
They have the same value.
They have the same, okay, they have the same value, the same amount. What about on the bottom? By the way, this sign right here is like a fish. Like a fish, or I don't know what you call it. I think of a fish when I look at it. You know, what's the mathematical meaning of that?
I have no idea.
Okay,
A
good. I
alpha
like yeah, no, I really like it. What I hate when people just, I don't want to answer, I'm scared. No, if you don't know, that's okay. It's okay not to know, but once you're taught, then you got to know. So in math, this is the sign of proportionality. It's different than that. This is A equals B. A and B are the same. I can change places, they're equal. But here it says A is proportional to B, and I really want to use the word direct. A is directly proportional to B. A is directly proportional to B. Now I'm sure you heard of that, this idea of proportionality, but what does it mean? What does it mean to say one quantity is directly proportional to another quantity? What does that mean?
When one changes, so does the other.
When one changes, the other changes, but not just that. When the one changes, the other changes exactly the same way. If two things are not the same amount, but they change the same way. So here's what I'm saying. If I increase, if this is a true statement, A is proportional to B. If I increase B, then I increase A. If I decrease B, I decrease A. If I double B, I double A. If I cut B in half, A gets cut in half. Whatever I do to one quantity, the other one's going to follow the same way. Now, how do you know when two quantities are directly proportional? Well, both of those quantities will either be both in the numerator or both in the denominator. And so when I look at Ohm's law, I see that I and V are both in the numerator, because remember, I can make this as a fraction. And so in the numerator here, I have a I, the numerator here, I have a V. So what I want to say is, I can say V, actually, I is directly proportional to V. I is directly proportional to V. Now, whenever I talk about something like this, the math stuff, when I talk about any kind of math, I want you to understand the math. If I say, do you understand this? You can shake it, yeah, I get it. But I also want you to have a gut feeling for what I'm talking about from the physics. You got to understand it from the point of view of the physics. So these two things are directly proportional, these two quantities. What that means is, if I increase the voltage, the current's going to increase. If I decrease the voltage, the current's going to decrease. Now remember, we said that one kind of cheesy way to think of voltage, we know voltage is really an electrical potential difference. It deals with the electric field, all that high power stuff we talked about last week. But simply speaking, voltage is the force or pressure that makes electrons move. And it should make sense that if I'm applying a force on something and making it move, if I have a stronger, bigger force, the thing's going to move more. It's going to move more and more and more. So if I increase the force, pressure, or voltage, I would expect to get more current. If I decrease that voltage, I expect to get less current. If I double the voltage, that's going to double the current. If I cut the voltage in half, my current's going to be cut in half. And that's assuming I'm not messing with R. R stays constant. So it's important. It's more, to me, it's more important to understand this relationship between I and V than it is to get an actual answer with the equation. The relationship is really important because it can tell you a whole lot. Remember the first week, the first sentence of the first day, we said that math is the language of science and engineering, and that we're going to have these equations speaking to us. I want to know, what are these equations saying? Well, this is one way of speaking, having the equation speak to us. When we look at the relationship between these variables, you should be able to right away look at this and say, in this equation, I and V are directly proportional to each other. They're directly related. It's not enough to say they're directly proportional. You have to know what it means to say one quantity is directly proportional to another. And I got news for you. I think I told you guys, my two most favorite persons in the world, number one is my grandmother, passed away in 1996. But second to my grandmother is I love me some Einstein. I love Albert Einstein. And Einstein said that if you can't explain it to a child, you don't know what you're talking about. If you cannot explain it to a child, you don't know what you're talking about. If you think about that, he's right. You have all these high-powered big concepts and these big words you use, but if you know the meaning of each word, you should be able to break it down to the point that where a kid can understand it. When you can do that, then you know what you're talking about. So, understand what these equations are saying. Well, okay, I see that. I kind of get the sign of proportionality. You said that if I have A proportional to B, that means whatever I do to one quantity, the other will follow the same way. What if I write it this way? What if I say that A is not directly proportional to B, but directly proportional to 1 over B? And the way you would say that is you would say A is inversely proportional to B, or B is inversely proportional to A. What do you think that means when I write it like that?
That the resistance.
When A goes twice, B will go down half.
Okay. So, yeah, I think both answers were correct. When I write it this way, with one quantity in the numerator and the other in the denominator, then what that means is whatever I do to one quantity, the opposite is going to happen to the other. So if I decrease B, A is going to increase. If I increase B, A is going to decrease. If I double B, that has the effect of cutting A in half. If I cut B in half, that has the effect of doubling A. And so you have this kind of relationship when you have one quantity in the numerator and the other one in the denominator. like I and R. So if I want to write this, I can say that current is inversely proportional to resistance. So if I increase the resistance, if I make it harder for current to go through a material, I will expect less current to flow through. If I decrease the resistance, I expect more current to flow through. If I double resistance, I'm only going to get half the current. If I cut the resistance in half, that's going to double the current. The relationship between I and R is what's important. In my mind, more important than the actual answer you'll get from using that equation. So you got a big job in front of you. Not only do you have to remember the three forms of these equations, really you don't remember, just remember this one, but know how to solve for V and for R. But also you got to remember the relationship between variables. And it's simple. If I have quantities in the numerator, then they're directly proportional to each other. If both are in the denominator, they're directly proportional to each other. If one is in the numerator and one is in the denominator, then they're inversely proportional to each other or indirectly proportional to each other. But you got to know what that means. When I use the word directly proportional or inversely proportional, you have to know exactly what that means. So, question over Ohm's law. Questions or comments? The best way to understand, the answers and the way we're going to do our calculations here is just to work examples. So here's what I want you to do. At the beginning of class today, I showed you some graphic symbols you can use to represent each of those quantities. I showed you 3 ways to represent a voltage. I showed you 2 ways to represent a current, electron flow, conventional current flow. I showed you the symbol that we use for resistance. So if you look at the first problem statement, let me share the topic sheet with you in case you don't have your topic sheet. I'll share my topic sheet with you. Now, in the upper left-hand corner of your screen, you'll see a little box with a magnifying glass on it, and you're able to zoom in on that document and make it bigger if you need to. But I'm looking at the topic sheet, and there are some problems at the very bottom of the topic sheet, some practice problems. And the first 3 under Ohm's law, those are the 3 I want to do. But what I was saying was I gave you symbols, these symbols you can use to represent voltage, current, and resistance. So what I want you to do is, number 1, read the problem. And if you have to read it a couple times, do so. Make sure you understand what's being asked. And once you understand the problem, I want you to try, from the problem statement, try to draw a diagram that represents the circuit. And let me switch off back to the camera for just a second. So we're going to try to draw, and actually you have symbols, right, for voltage. We can use this, we can use this, we can use this, right, for voltage. We can use for current the arrow. For resistance, we use this. But what if you have a device and you don't know what the symbol is for? You don't know what the graphic symbol is for. If it's something that they mentioned in the problem and you don't know what it is, what you can do is just draw a box and label it whatever they call it. If it's a phone, a cell phone, you might just say phone. But all electrical devices have 2 terminals, 2 power terminals. So no matter what it is, you got to draw 2 wires coming out of it like this. So everything has 2 terminals. So use these for voltages, current, resistance, and if it's something you don't know what it is, just draw a box and label it. Whatever they call it, label it. So I'm going to go back to that document. What I want you to do is to get a sheet of paper, get a pencil, pen, coloring pens, pencil, whatever you have, your calculator, and read the problem and understand what's being asked. What I like to do is I make a list of what I know and what I'm looking for. I read the problem, make a list of the knowns or the givens, and then what I'm looking for. And from that list, that'll point me to the right equation. And then once I use the right equation, I write the equation, put the numbers in it, get my answer, and check to see if my answer is correct. So I'm going to share that document with you, and I'm going to give you a few minutes. I want you to read problem number 1, draw the schematic. Don't skip over this part. It's important that you start drawing these diagrams. Draw the schematic, what you think the schematic will look like for problem number 1, and then solve it, and then we'll go back on camera and we'll solve it together, and then I'll let you do the other 2. So, here you go, problem number 1 on the topic sheet. Give you about another minute, and I want to talk about this problem. All right, so the problem statement, you have a 100 volt battery. It's connected to a 20,000 ohm resistor and wants you to find the current. So what I did, I made a list of what I know and what I'm looking for. I know the voltage is 100 volts. I know the resistance is 20,000 ohms. And I know that I'm looking for the current given voltage and resistance. So this right here is going to tell me which equation to use. I want to know I equals something. Well, I is going to equal V over R. But before you get to that step, it's important that you can draw the circuit, the schematic that represents the problem statement. That's very important in this class. Draw the schematic that represents the problem statement. The schematic is just a pictorial way of representing the problem. Given the symbols I gave you at the start of the class, I have a voltage of 100, so I'll use one of those symbols to represent a voltage source. Resistance is 20,000. So here's a symbol for a resistor. Now, they have it written as 20,000, but we would never write it that way. We know 20,000 is 20 times 10 to the third ohms. And I can replace that with 20, and it'll be kilo ohms. So this is the way an engineer will write it. So this is 20 K ohms. If you wrote it like this or like this, it's not wrong. I mean, it's okay. But that's kind of like going to the store buying something that costs $1 and you give the person 100 pennies. It's $1, but they're going to look at you real funny. So, you know, you want to show this to an engineer when you're talking to other engineering buddies. You want to show it that way. Now I'm going to connect these with wires. And this is a representation of the problem statement. And all I got to do now is write in what I'm looking for. And I'm looking for current. So I'm going to show a current arrow with a question mark. And so this list right here says I'm looking for what is I equal to? Well, that's this one. So I'm just going to write that equation down. Now, when you do work for me, and if you've done it a different way up until tonight, I don't really care about that. But from tonight going forward, I don't care how simple you think the problem is. I want you to always start with the problems with the working equation, and then the next step will be the equation with the numbers in it, and the final step will be your answer. So what I'm saying is, don't just give me the answer. I want to see what equation did you use. All right, Ron, I use this one. I use I equals V over R, and then you're going to say equals. Well, V is 100, and R is 20. And I know, now if you do it this way, it's real simple, right? Then if you write it like that, 20,000. That's just 100 divided by 20, which is 5. And then now you got to remember that K is 10 to the third. So you have K is 10 to the third, and milli is 10 to the minus third. And remember, for math, if you have A to the n, it's equal to 1 over A to the minus n. Or if you have A to the minus n, it's equal to 1 over A to the n. So, you know, whatever's on the bottom that comes to the top is a negative, right? If you have that when you do your law of exponents. Well, here I have K on the bottom. So I have 1 over K. But 1 over K is 1 over 10 to the third. So if I have 1 over something that's positive, when I divide that, it comes up as a negative. So this will come up as 10 to the minus third. If I have 1 over 10 to the minus third, it will come up as 10 to the third. So a K, the thing to remember, anytime K is on the bottom, if I have 1 over K, my answer is going to be in milli. If I have 1 over milli, my answer is going to be in K. So if you remember that, then I say, all right, well, if I cover that up, I got 100 divided by 20. That's easy. That's 5. I know my quantity is current, so current's going to be in amps. But since I have 1 over K, 1 over K, 1 over 10 to the third is 10 to the minus third, and 10 to the minus third is a milli. 1 over k is a milli. So this is not 5 amps, it's 5 milliamps. Now, the way I said it, it took a long time, but you should be able to do that in seconds, in microseconds. It should be pretty easy. So I have the problem, the thing I'm looking for, the working equation, put the numbers in, give me your answer, and then you probably, if this is homework or a quiz, you probably want to circle your answer so I can find it quickly. Okay, so anybody have any questions on the first problem? Okay, well, it's like almost 5 after 7. What I want to do is I want to go through the first section of the topic sheet tonight, which is Ohm's Law, and then we'll take a break for a few minutes. So I'll put the document back up on Blackboard, share it with you again. I now want you to do problem number 2, the second problem on the page. Give you about 1 more minute, and I want to go over the problem. All right, so for problem number 2, since you have a relay, it operates at 48 volts and it draws 30 milliamps of current. They want to know the resistance of the relay. So you have a choice here when you make your circuit diagram. You can either draw your circuit like this. And you can draw a resistor over here. Maybe call it R relay. Or if you want to, if you don't know what the schematic symbol for a relay looks like, you can do what I said before, just draw a box. Call it relay. So either one is okay. But we have a voltage source of 48 volts. I know my current is 30 milliamps. And I don't know my resistance. I want to know what is the resistance of the relay. So I'm looking for R equals something. Well, that's that. So I'm going to write down my equation. R equals V over I. I'm going to substitute my value for V and for I. So for V, 48 volts. I'm not going to write this out as 0.03. I'm going to just write 30 milliamps. And I'm going to use the idea that I used before. I'll cover that up. I got 48 divided by 30. Now, anybody have a calculator, tell me what is 48 divided by 30. How much is that?
1.6.
1.6. 48 divided by 30. I know I'm looking for resistance. Resistance has the units of ohms. So I'm going to have an ohm. I got 1 over milli. If I have 1 over milli, it comes up as a kilo. If I have 1 over kilo, it comes up as a milli. So it's a milli on the bottom. This will be K ohm. So it's 1.6 K ohm. The resistance of that relay is 1.6 K ohm, 1,600 ohms. Questions or comments on problem number 2?
So would you want it to be written as 1.6K or the 1600 ohms? Either way works, right?
Either way works.
Okay, perfect.
Okay? All right, well, we got one more problem to do, then we'll take a little break. I'm going to share the document with you again, do that last problem, and then we'll take a break for a few minutes, and then we'll come back and we'll talk about the next topic and right after the break. So here you go. Here's the sheet, and we're looking at problem number 3. You guys can give about 1 more minute and we'll go over the problem. All right, so problem number 3. An ammeter has an internal resistance of 5 ohms. If 5 milliamps of current flows through the meter, find the voltage across the meter. Find the voltage drop across it. What's that all about? Well, a couple things here. It mentions an internal resistance. What does that mean, internal resistance? So when you talk about the internal resistance of a device, what you mean is you mean the resistance inside the device, but it doesn't necessarily mean there's a resistor that's in the device that's 5 ohms. What they mean is the resistance of everything in the machine, in this case the meter, the resistance of everything that makes up the meter is 5. We call that the internal resistance. So just lump that into one symbol and you can call it 5. So when I make a meter, I make it either a square or a circle. So I'm just going to represent my meter like this. That's an ammeter.
Hello, could you please switch the screen?
Oh, I'm sorry. I forgot to unshare my document. So I was showing you I would make an ammeter like this, just a circle. Now it said it had an internal resistance of 5 ohms. So the way you show any kind of resistance is using the resistance symbol. So I'm just going to show that symbol like this and say that that resistance is 5 ohms. Now when I'm showing this symbol for a meter, this is not a standard symbol. This is just the way I do it. I'm not even sure that there's a standard way to draw a meter. Typically they'll just draw a circle and label it ammeter or voltmeter, ohm meter, or they'll draw a square to represent a meter. So basically I have, and I'm not going to show the whole circuit here. I got this device, the ammeter. I know the resistance inside the ammeter is 5 ohms. And I also know I have 5 milliamps of current flowing into the meter. And what I want to know is, what is the voltage across the meter? I measure from here to here, across that meter. What will the voltage be across that meter? And the way you get that is I need V equals something. Well, that's this one. V equals I times R. So I want to start by saying V equals I times R. I is 5 milliamps. R is 5 ohms. Now notice I left this as milli. I didn't write that as 0.005. I left it as milli. The only time I would write that as a decimal is if this was in something other than ohms, I might write it as a decimal. But typically I just leave these as they are, the K and the M's. Sometimes you can get things to cancel out if you, and I'll just show you that. Well, I'll show you that later on. I don't want to get too much off track here. Anyway, I got 5 times 5, which is 25. This is voltage, so the units for voltage is the volt. And since this is in millis and this is in whole units, this would be millivolts. So I will read 25 millivolts across that meter, and then I'm done. One thing I would have to do here, if this was a test or quiz, put a circle around my answer so I know where to look, and then you're good to go. So this is our first stab at Ohm's law. You can see that it's pretty simple to do. Just once you figure out what you're looking for and what you're given, that points you to the right equation. So these problems are simple, but what you want to practice doing that might not be so simple is just start drawing these diagrams to get used to drawing. Sometimes students will be fast to just write the equation down and give the answer. And then when they come in here and I speak with the diagram, they don't know how to draw the diagram, or they don't know what my diagram represents because they haven't practiced at home. So as you do the homework, I haven't put the homework problems up yet, but I will. When I put those up, make sure you go through, try to draw a picture, a schematic for the problems that it's easy to draw a schematic for. That way you get used to them. Anybody have any questions over Ohm's law? Any questions, concepts, thoughts on the first part of the lecture? Okay, if there's no questions, and I'll have time at the end if you think of something. I'll stick around after class, and I'll be happy to answer any questions. Just jot them down, and I will address those at the end. So what I want to do now is take a break, 5-6 minutes, and I'll be off camera. We'll take a break for maybe 5-6 minutes, and then we'll come back and we'll talk about energy and power. So take a break, come back in about 6 minutes, and we'll continue. Okay, guys, we'll start up in about 60 seconds. 1 minute. All right. Next topic, I want to talk about power. So far we've talked about voltage, separation of charge. We talked about current, charge and motion, and we talked about resistance, opposition to current flow. Next, we're going to talk about power. So what is power? When you think about power, tell me what you think of. What is power?
Transferred energy.
Power is transferred energy. Okay, I think I like that one. Anybody else? Okay, well, we'll go. Nobody else?
That's what I would say too.
Okay,
Energy changing states.
all right. Well, let me give you two definitions that we'll use in this class for power, and which way you think about it depends on the problem you're trying to solve. So power, the first way to think about it, it's a rate of doing work. It's a rate of doing work. So what's a rate? Well, it's like how fast you can do something in a certain amount of time. So let's say I have two motors. Each motor it hooks up to exactly the same voltage, maybe 120 volts. One motor is a 5 horsepower motor. The second motor is a 10 horsepower motor. Well, what that means is that the 10 horsepower motor can do twice the amount of work as a 5 horsepower motor in the same amount of time. So how much is a rate of doing work? And remember, for work to be done, something has to move. The second way to think about power, it's also a rate of converting energy from one form to another. So an example of that might be a light bulb. Maybe you have an incandescent light bulb, a 100-watt light bulb. What does it mean? What is 100 watts? What does that mean? Well, you're converting energy from one form to another. You're converting electrical energy to light energy. And so how fast or the rate that you're doing that is another way to think about power. So we'll think about power as a rate of doing work or as a rate of converting energy from one form to another. Either way, it's okay. Now, anytime in physics you have rate, when you see that, they often mean a time rate. And what a time rate is when you want to show something moving, it's always divided by time. So if I want to talk about the speed of something or velocity, it will be distance over time. Maybe I go 100 miles in 2 hours. So your velocity or speed would be 50 miles per hour. That's a time rate. And so in physics, we have a lot of time rates. And so it's the same with power. So I'm going to write the expression. So power, one way is if I use this rate of doing work. So power would be work per unit time, or power will be energy converted per unit time. So either way you want to write it. If you write it this way, we'll say that P equals, and we'll use that W over T for work, or here, P equals E over T. Notice both of those are time rates. Now, if you remember what we said in the last class was the unit for energy is the joule, and the unit for work is the same as the joule. We use seconds for time. So in both cases, the unit for power is the joule per second. The joule per second. And what we do is, remember for volts, we had a joule. For coulomb, we define that as 1 volt. Or we had a coulomb per second, we define that as 1 amp. But now we're going to take a joule second, we'll call that 1 watt. So power for us is given in watts, and 1 watt is 1 joule every second. 1 joule of energy converted from one form to another, or 1 joule of work done. Either way, a joule second is a watt. We don't usually write it out like that, although you can. Typically, just use the capital W. So 1 joule second is a watt. Named after James Watts, the physicist James Watts. So now the problem is defining power as work over time or energy converted over time. I'm looking around the lab and I don't see any energy meters in here. There's no way to measure the work or energy being done in the circuit. So that's not a very good thing. It'd be nice if we had a way to calculate power from the 3 fundamental quantities that we study, from voltage, from current, resistance. It'd be nice if we can do that. So let's see if we can figure that out. Turns out that if you take the product of voltage and current, you get power, and this is called Watt's law. Watt says that power equals voltage times current. And if you remember, if you did the supplementary quiz, if you did that already, or if you paid attention to the lecture from last week, and I mentioned it this week, the unit for voltage is a joule per coulomb. And the unit for current is a coulomb per second. So since I'm multiplying volts times current, I'm really multiplying joules per coulomb times coulomb per second. And you can see what's going to happen here. If I do that, then this is going to drop out, and I'm going to be left with joules on the top and seconds on the bottom. So that right there is the units for that thing. And we already know that's correct because we said power is in joules per second. So by multiplying V times I, I'm really getting joules per second. So I'm really getting power. So the way we're going to calculate power is by taking P equals V times I, and that is called Watt's law. Now, what you could do though is this. We can combine Watt's law and Ohm's law and get some new equations that we can use over there for power, which might be helpful. So what I'm saying is, since I know from our last discussion, I know that I equals V over R. I know that V equals I times R, and I know that R equals V over I. That's Ohm's law. So what I could do, I could take P equals, and now I'm going to take, instead of writing V, I'm going to write what V is equal to from over here in Ohm's law. I see that V is equal to this, I times R. So instead of writing net V, since I know V is equal to I times R, I'm going to substitute I times R for V and bring down that I. So I got P equals V, but V is I times R times I. So P equals I times I is I squared, and get that equation. That's another way to write Watt's law. P equals I squared times R. Now that's kind of nice because, see, here, if I want to find the power in the circuit, I got to know the voltage and the current. Well, maybe I don't know the voltage and the current. Maybe I know the current and the resistance instead. I can still get power. Or maybe instead of substituting for V, what about substitute for I? What would that give me? Well, let's figure it out. I get P equals V times I, but I is equal to this. So for that I want to substitute V over R. And now when I multiply this out, I get V times V, which is V squared over R. I get P equals V squared over R. So there's another way to write it. Power is P equals V squared over R. So maybe I don't know, maybe I know V and R, and I don't know I can still get power. No matter which one, no matter which two quantities I know of the big three, I can always calculate power if I write down each form of Watt's law. Just realize that this is the fundamental way or the standard way of writing it right there. The other two are just substitutions, we get the other two equations. So what I would do, guys, if I were you, I gave you 3 forms of Ohm's law and now 3 forms of Watt's law, just somewhere all in the same place. Just write all these equations down so you have them handy. You can just kind of look at them and use them as you need. Okay, so we define power as a rate of doing work or a rate of converting energy from one form to another. I showed you equations for both of those physics equations. P equals E over T and P equals W over T, where E is for energy and W is for work. We talked about what it means to have a time rate of change. That means T is on the bottom. The unit for power is a joule per second, but we define the joule per second to be 1 watt. And then we figured out that if I take the product of V and I, we still get joules per second. So that looks like the product of V and I really does give me power because the units work out. And then we use Ohm's law on that basic power equation, P equals V times I. We did substitutions on V, we did substitutions on I, and we were able to come up with those other 2 equations. And now we have a way to calculate power, no matter which 2 of the big 3, voltage, current, resistance, no matter which 2 of those I know, I can always calculate the power. Okay, so what I want to do now is go back to the topic sheet, and in the power section, there are three questions. Question number 4, 5, and 6. And we'll do number 4, and I'll put this back up on the camera in a second. We'll do number 4 together, and then once we do number 4, then I'll give you time to do number 5 and 6, and we'll knock those out the box and get those done. Now for these 3, I don't mind if you don't have to draw pictures. You can if you want to, but I'm not going to draw pictures on the board. Schematics for 4, 5, and 6. Let me put the sheet back on the board. You can read the problem statement. We're doing problem number 4 on the topic sheet if you have your sheet available. If not, here you go. I'm sharing it right now. Problem number 4. Okay, so for problem number 4, it says you have a clothes dryer. Excuse me. You have a clothes dryer. It draws 15 amps of current from a 220 volt line. They want you to calculate the power used. So how would you calculate the power used? So I've made a list here. Always, when you're solving these problems, make a list of what you know and what you're looking for, and that list will point to the correct equation. I need an equation with a P, a V, and an I in it. P, V, I, that's the first one. So I'm going to start by writing P equals V times I. I'm going to put my number in for V, which is 220 volts. For I, it's 15 amps. And if somebody could take the calculator, tell me what 22 times 15 is, how much is that?
3,300,
How much?
3.3 kilowatt,
3,300
3.
watts. Divide that by 1,000, 3.3 kilowatts. So either one of these way of writing that is okay. This is probably the preferred way. Okay? So I'm going to share the document with you again, and then we have problem number 5 and 6. I'll leave the camera up, this document up for a minute. I want you to do problem number 5, and when you get done with that, go ahead and do number 6, and then we'll move on to the next topic. I'll share the document with you now. Okay, so we'll give you about 1 more minute, and then I want to talk about these 2 problems. 1 minute. All right, so let's look at problem number 5. You have a 27 ohm resistor. The resistor has 20 milliamps of current flowing through it. I want you to calculate the power dissipation. That word dissipation is one that you'll hear often in electronics. We talk about the power dissipation of a resistor. We're talking about the amount of energy being converted from electrical energy to heat energy. So it dissipates power. R is 27 ohms. I is 20 milliamps. I want no power. I make a list of what I'm given and what I know. I need, this looks like rest in peace, right? RIP. I need an equation with an R, an I, and a P in it. So it'll be that second one right there. So that's my working equation. So I write the equation. P is I squared R. I will then put the numbers in for I and for R. Now, earlier I said that I always leave the K as kilo, I leave it as a K, and the M as a milli, I leave it as an M. Well, the exception to that is anytime I'm taking the square root or I'm squaring a number that's in K or milli, I always write it in decimal. If you're using the calculator, you put in your calculator the right way, it won't make a difference. But I usually do this kind of, by hand. So what I'm saying is instead of writing this as 20 milliamps squared, I'm going to write this as 0.02 amps squared. And I'm going to convert it at the end to milliwatts, kilowatts, or whatever it turns out to be. So I got I squared, 0.02 squared, times R, which is 27 ohms. So if you have your calculator, somebody calculate for me 0.2 squared times 27, and let me know what you get for an answer. 0.2 squared times 27. How much is that? Somebody said it was 1.08.
Yeah, sorry, I would have said it. I have like a canker sore right now and it kills. I bit my lip the other day.
I don't know if that was meant for us or not. Let me see who that is.
It was me. Can you hear me?
Was that Michael?
Yeah, I was saying I would have just said my answer, but I have this canker sore, so that's why I haven't been talking. I'm not trying to not participate in
All
that.
right. So I got a Michael, I got a Mike who's gonna be, and you guys are right on this thing together. I got a Michael and a Mike. So what happens if you take 0.02 and square it and multiply that by 27? Somebody said it was 1.08, but I think that decimals are wrong.
0.0108.
Okay? So 0.0108 watts. And you probably want to write that as milliwatts. So if I move this over 3 places, it will be 10.8 milliwatts. Now you can leave it like this. I don't care if you leave it like that. but you should be able to convert it to this if I ask you to. Okay? So I think whoever texted me that answer, you were off by 1 decimal point. Maybe you put it on you typed it in wrong or something, but there you go. So as I said before, the only time I take that and write it as a decimal is when I'm squaring, taking the square root of a m or a k, then I'll write it as a decimal. So that was problem number 5. Anybody have any questions over that problem, number 5? Well, number 6 is right here. It says that you have a certain device that has 10 volts across its terminals, and it has a resistance of 20 ohms. They want you to find the power. So I made a list. And from the list, we'll determine I need a V, a R, and a P. V, R, P, that's the third equation. I'm going to use that one to solve that problem. So I got P, V squared over R. V is 10. R is 20. On the top, when I square it, I'll get 100 over 20. So that'll give me 5. And my units would be watts. How would I write this as kilowatts? How would I write 5 watts as kilowatts?
0.005.
Right. So it's important. It's very important to be able to convert from watts to kilowatts. It's really simple. Just take the number you want to convert to kilowatts, divide by 1,000. If you divide by 1,000, then you move the decimal place over 3 places. So 5 on 1,000, 3 places, 0.005 kilowatts. So you want to be able to do that. So there is problem number 6. And each of those problems demonstrated the use of Watt's law in one of all 3 forms. So questions over problem number 6 or any of the problems I've talked about so far? Anybody have any questions?
So for this problem, do we need to draw circuit diagrams?
You guys, I want you guys to get used to drawing the diagrams. So what I would suggest is that most of the time on the board, I'll draw them. I mean, it's going to reach a point to where probably after next week, you really won't be able to solve a problem without drawing the picture first. I mean, unless you're Einstein. So what I would say is just get used to drawing the problems, and anytime you can draw a schematic easily, just do it. Just kind of by nature, you're gonna do it because there won't be any way to solve it without drawing. You'll have to draw it. So just get used to drawing it. Practice as much as you can. If it's one that you can get through without drawing a problem, you can go ahead and do that. I don't mind. But like I said, after this week, you'll be stuck with drawing these problems, and your schematics will be more complicated because as we go through the course, you'll learn more and more symbols and what the symbols mean. So we kind of work off those pictures. So I highly recommend you guys draw pictures when you can. Any more questions or comments? All right, well, I want to move to the final topic for tonight. I want to talk about energy. I want to talk about energy calculations, and then there's a couple other terms, efficiency and transducers. What do those terms mean? So let's get into that. Let's write down what we looked at so far this week and last week. So last week we talked about voltage, current, resistance. And in explaining voltage, we talked about energy. And then this week, about power. So these are all the electrical terms we've talked about up to this point. Voltage, current, resistance, energy, power. So just kind of briefly, we said voltage is a separation of charge that gives us an electrical potential difference. You can think of it as the pressure or force to make electrons move. Current is the flow of charge. Resistance is the opposition to that current flow. We said energy, well, energy is kind of hard to think about. We said energy is ability to do work. If you have something moving, then that thing has kinetic energy, and kinetic energy can actually do work. Potential energy is just stored energy that you can change to kinetic if you want to make work happen. And then there's power. We said power is a rate of doing work, or power is a rate of converting energy from one form to another. So we gave the quantity, and now you have kind of a definition or explanation for each quantity. So I want to ask you a question. Of the 5 quantities I have on the board, voltage, current, resistance, energy, power, which of the 5 do you pay for? When you pay, what are you paying for? Are you
Energy.
paying for You're paying for energy?
You're paying
got
for
one.
power. You're paying by the watt.
Okay. Okay, well, let's do this. Because the argument is never this. Most students know we're not paying for voltage, so we might as well just cross that out. No, you're not paying for voltage. You're not paying for current. Thank God we're not paying for resistance, because resistance values are usually really high. So it usually boils down to those two. You're either paying for energy or you're paying for power. One of these you're paying for. Okay, well, now I know some of you are still at home and you live with your parents, so you probably never paid an electric bill before in your life, but just keep living. You will. Trust me, you will. When you pay your electric bill, how do they know how much to charge you?
By the kilowatt hour.
By the kilowatt hour. Where'd you get that from?
My electric bill.
Your electric bill. So, guys, you may not have ever looked at this before in your life. I don't know. I just said energy because Duke Energy. So somebody said energy because it's Duke Energy. Okay, well, that was kind of smart. Look at this though. The electric meter. This is what you find either outside your house, if you follow the power wire to your house. If your meter's outside your house, if you follow the power wire from the telephone pole, if you have an overhead connector, power line running to your house down, you'll go to this meter. Looks kind of like this. This is the old type of meter. The new ones are digital or LCD, and the newer ones than that, they don't even have a screen on them. They're just a little black box. But this meter will either be on the side of your house on the outside or in your basement, maybe in your basement near your circuit breakers. Somewhere this meter is living. It's at your house somewhere. And if you look at the meter, you'll notice a couple things. Number one, there's a bunch of dials on here, right? There's a dial right here. There's a dial right here. You got all these dials. Now, the new ones don't have these dials. They have digits. They're digital. But this is, when I grew up, meters looked like this. And what will happen is you would get, there was actually a person called there was a meter man. I guess now it's the meter man or meter woman. But back in the day when I was growing up, it was a meter man. They would actually come out to your house and they had to go in your house and read your electric meter. And that's what this is, electric meter. And what they were reading, they were looking at these hands to see what number they pointed to. So like for here, this is pointing to, I can't see what the digits is, but these will point to these different digits. And they would write it down. Maybe it's a 1 and a 3 and a 2 and a 4. I'm just making this up. So they would read these digits, and maybe this was they came out in the month of February, and they wrote down these digits off this meter. And then what they would do is they would come back next month, they come back in March, and they would read the digits again. So they get a reading in March for each of these digits. I'm just putting X's there now because it's faster. They come out and they get a reading in March. And what they would do is they take the reading from February and the reading from March, and they would subtract the two from each other, and then we'll get some numbers down here. And that difference would be the amount of whatever this meter is reading, that's the amount of it that you use. They subtract these two. Well, what is the meter reading? Well, somebody already mentioned the term kilowatt hour. So this right here, this unit is what this meter is reading. Kilowatt hours. Kilowatt hours. So to answer the question, what are we paying for? We have to know or figure out what the heck is this meter measuring. We know it's measuring kilowatt hour, but what the heck is a kilowatt hour? So that'll help us answer the question, what are we paying for? Because this is how they determine what you're paying for. And so it turns out that a kilowatt hour is just the product of kilowatts and hours. In other words, if I take the number of kilowatts and I multiply that by the number of hours I'm using those kilowatts, that's what this meter, or that meter I just showed you, that's what we're measuring. Now, I mentioned to you that that's what the meter looked like when I was a kid. They'd come out to your house, and actually they would write those numbers down. Nowadays, they don't do that anymore. Nowadays, it's all done via the internet. They come through and actually can they can remotely read your meter. They can also remotely read it, remotely turn it off and turn it on. You might know now that they don't have to come out to your house anymore to turn your electric on. They can just push a button and it's on, push a button and it's off. So guys, you young guys out there who haven't paid any electric bills yet, when you get an electric bill and you don't pay your bill, they push a button and they turn you off. And then what you got to do to get it turned back on, you call down, you got to pay your past due balance, but then you have to pay something called a reconnection fee. So what is a reconnection fee? Well, it used to be back in the day, like when I was a kid, when they disconnect your power, they actually have to drive out to your house. They go up on the telephone pole and they would physically disconnect the wire that connected the grid to your house. They would just basically unplug you at the telephone pole. Well, to turn your power back on, they had to pay a guy, Duke Energy had to pay a guy to come back out to your house, put the ladder back up there and reconnect that wire. So they would charge you a reconnection fee. That's where that term reconnection fee came from. Well, they don't do that anymore. They don't send a guy or person out to your house. They just push a button and it's all done electronically at your meter. So when you pay the reconnection fee, now what you're just paying, that's just pure money for Duke Energy because there is no reconnection fee. It doesn't cost them anything to push that button. So that's something that then went away. The term, the actual coming out to the telephone pole went away, but the charge that they charge you for doing it, that didn't go away. And somebody ought to be upset about that. It's one of the things in life that really pisses me off, the reconnection fee. But anyway, that's not what you're here for, to hear about my problems. You want to know about kilowatt hours. What is a kilowatt hour? What physical quantity does this represent, a kilowatt hour? Now, it looks like if I study this, I'm taking kilowatts, which is power. This right here, that term, or that factor is power. And I'm multiplying it by this factor right here, which is time. So the question is, if I take power and I multiply by time, what kind of physical quantity do I get? Which of these do I get? And to answer that, remember what we said about power. We said that power is energy per unit time. So power is energy per unit time. If I multiply energy per unit time by time, and you can see what's going to happen. These are going to cancel out, and the thing I'm going to get over here is energy. So, I don't know who said it, but whoever said you pay for power, the reason you said that is because you're probably not a really young person. You're probably older like me. And back in the day, we called Duke Energy the power company. And I want my power turned on. What you're really getting turned on, you want your energy back. You pay for energy. We do not pay for power. You pay for energy. Well, how do you know how much to pay for energy? Well, it's kind of like this. You know, when you drive your car, you look at the gas stations and you figure out the cost of gas per gallon. You can figure out the cost of gas per gallon. And if you know the cost of gas per gallon, and you know the number of gallons of your gas tank, then if you know how big your gas tank is, and you know the cost of gas per gallon, you can multiply these two together, and you see what's going to happen? You'll get how much it costs to fill your tank up. I take the cost of gas per gallon times the number of gallons my gas tank will hold. That's how much I got to pay to fill my tank up. That'll be my cost of energy. Well, it turns out you can do exactly the same thing for electrical energy. Only we don't want the cost per gallon. We want the cost per, they charge you for these, kilowatt hours. So we want the cost per kilowatt hour. If you know the cost per kilowatt hour and you know how many kilowatts you've used, you can multiply those two together just like you could here, and you can figure out how much you got to pay for electrical energy on your electric bill. Now, how do you figure out the cost per kilowatt hour? Well, that's easy. You have choices. The easiest way is to get your electric bill and look at it. It'll tell you how much you're paying per kilowatt hour of electrical energy. Another way to do it is just to get on YouTube, not YouTube, but Google, and just Google it. Some kind of way, the cost you're being charged per kilowatt hour is available to you. So that's important because I don't know if you looked on your Blackboard, but remember last week I gave you a homework. There was a supplementary quiz. Well, I gave you another one this week. Only it's not a supplementary quiz. It's called an energy project. I'll bring that up here in a second before we end class tonight. That's going to count as a quiz grade. So you want to make sure you look at that. But what I'm talking about now is going to help you to work problems on that energy project. So what you want to remember is when you see kilowatt hour, it's a unit of energy. A kilowatt hour is not power, it's a unit of energy. I just proved that to you mathematically. If you accept the fact that kilowatt hours is the product of kilowatts times hours, then if you take power times time, you get energy. Now, I know what you're thinking. You're saying, well, Singleton, last week you said the unit of energy is the joule. You kept saying the unit of energy is the joule. Well, it is the joule. The unit of energy is the joule. But the thing about it is when you don't want your electric bill in joules. If your electric bill was written in joules, your electric bill would probably be about 10 feet long because you use a lot of joules in 30 days. So it's like when you go get gas for your car, you don't want them to measure gas in teaspoons. You drive to the gas station, hey, let me get 10,000 teaspoons of gas. That's silly. The meter would be that big. They have a bigger unit. Instead of using teaspoons, they use gallons. That makes more sense. Well, the same way with a joule is too small to measure for energy going into a house over a 30-day period. So they have a bigger chunk of energy, a kilowatt hour. You can figure out how many joules equals 1 kilowatt hour if you want to. You can do the math. It's pretty easy to do. Just remember, a kilowatt hour is a unit of, not power, it's a unit of energy. And I just proved it to you. And I always say kilowatt hours of energy just to emphasize the fact that this is energy and not power. So here's what we're going to do. We're going to do some energy calculations now. And what I want to do is I'm going to give you the cost of energy. Now, the cost of energy at Duke, and depending on where you live, you may live in Indiana, Kentucky, it varies from where you live and different companies, they charge different amounts. In this class, what we're going to use is for cost of energy, 10 cents per kilowatt hour. So write that down somewhere. We're going to use 10 cents per kilowatt hour. And this is what we're going to use for cost of energy. But be clear, I'm not saying that's how much energy costs. I'm saying that's the number we're going to use for this class. I think that's kind of expensive. I think it should be a little less than 10 cents per kilowatt hour. But 10 is a nice number because it's easy to multiply by. So let's say I give you a quiz and it's an energy calculation, and I don't give you the cost of energy. Assume it's this. We're going to assume all throughout the semester that the cost of energy is 10 cents per kilowatt hour. Just realize when you go out in the real world, it's going to be a difference. It's going to depend on where you go and who's charging. Okay? So I'm going to be quiet for a second. I'm going to put this sheet back up, the topic sheet, and I want to look at problem number 7. And from what I just talked about, and just use a little logic, I want you to figure out or see if you can figure out problem number 7. So I'll put that up there, give you a few minutes to think about how you would solve it, and then I'll come back on the camera and we'll solve it together. So here is problem number 7. Let me share it with you. All right, see what you can do with problem number 7. I'll give you about 1 more minute, then I want to talk about this problem. So we got 1 minute. All right, so problem number 7. How much will it cost to run a 5-watt clock for 30 days? Anybody get an answer for this yet? How much will it cost? 5 watts for 30 days. How much will it?
It's probably wrong,
36
but
cents?
I got $360.
$360. What? Anybody else get a number?
36 cents?
36 cents.
36 cents. Anybody else get something different? This is interesting. The 3 and the 6 and the 3 and the 6. So that's interesting. Okay. So here's the good news is that once you understand a basic problem like this, all the other ones are pretty much done the same way. Somebody got 300. Michael says 360. So a couple people got this one. All these are pretty much done the same way. So here's the steps to solving a problem like this. Calculate the cost of energy. The first thing you want to do is convert all your watts to kilowatts and all your times to hours. So I got to convert 5 watts to kilowatts. I got to convert days to hours. You get the product of watts and kilowatts and hours, and that'll give you the number of kilowatt hours. And then you multiply that by the cost of energy. So step 1, convert this to kilowatts. Remember earlier I said the way you convert watts to kilowatts is by dividing by 1,000. If I divide this by 1,000, I'll end up with 0.005 kilowatts. And then I convert 30 days to hours. Anybody do that conversion? How many hours is that?
720.
720 hours. So you would say I got 30 days times 1 day is 24 hours. You cross that out, and that should give you 720. So we got 720. So what I would do, guys, is a couple things. For these problems, these energy calculations, number 1, I already mentioned, we're going to assume for this class, the cost of energy is 10 cents per kilowatt hour. Number 2, we're going to assume a month is 30 days. So we'll always assume a month is 30 days. Some months have 31 days. Some months have 28 days. It just depends on the month. For us in here, it's always 30 days. If I give you on the quiz, a month is 30 days, which means it's going to be 720 hours. So you might as well just remember the number 720. That'll come up. So once I convert my power to kilowatts, and make sure my times are in hours, then I just find the number of kilowatt hours. I'm multiplying kilowatts times hours. So for this one, I got 0.005 kilowatts. And we'll multiply that by 720 hours. So what is 0.005 times 720? How much is that?
3.6.
3.6. 3.6 what? 3.6 kilowatt hours of energy. This is energy here, 3.6 kilowatt hours of energy. So now to get costs, what you're gonna do is you'll say, all right, the cost is gonna be, if I know how many kilowatt hours I'm using 3.6 kilowatt hours. If I know how many I'm using, and I know how much Duke Energy is charging me, they're charging me 10 cents per kilowatt hour. Then I can figure out the cost. But one thing, I want the cost not in cents, I want the cost in dollars. So if I have 10 cents, how much of a dollar is 10 cents? 10 cents equals what?
0.1 dollar.
$0.1. So I want it in US dollars. So instead of having 10 cents, I'm going to put $0.1. That way, my answer will be in dollars and not cents. So if I do that, I see right away that the kilowatt hours are going to cancel out. My units will be in dollars, which is what I want. And the nice thing about multiplying by that 0.1, all you're going to do is move the decimal over one place. So if I take 3.6, then multiply it by 0.1, it's going to move the decimal over one place. That's going to give me 0.36, but that's in dollars. So $0.36 is actually 36 cents. And that makes sense. I don't think I want to pay $360 for a clock. You know those little small clocks with the hands on it that they glow at night? That little bitty clock. I don't think I want to pay $360 for that. That's a lot. They got you, but 36 cents, I'm okay with that. I'll pay 36 cents for that. So there are the steps for going through these energy calculations. They're all pretty much done the same way if you follow these steps. Sometimes they'll throw you a curveball, like they may not give you watts. You might have to figure it out, but you have all the equations to be able to figure out whatever they might ask you for. Number 8 is an example of that. So let me go back to the sheet. I'm going to switch the camera back. Before I do that, does anybody have any questions for me over this problem? Any questions or comments? Okay, well, I want you to try it again. Try number 8. Now that you've seen this, let's go to number 8, and I'll give you a few minutes to do number 8, and then we'll come back. And after we do number 8, I got just 2 more concepts I want to talk about, and then we'll finish out the sheet, and then we'll call it a night. We'll be done. Hopefully, we can get done here before 9 o'clock, but we'll see what happens. So here is problem number 8. I'm about to share my screen with you. And I'll give you a few minutes to work on it. Okay, guys, we'll give you about 2 more minutes on this one. 2 minutes, and then we'll talk about it. All right. Problem number 8. It says we have an electric heater that draws 5 amps of current from a 120 volt power line. How much will it cost to run this heater for 1 day? Did anybody get an answer?
$1.44.
Okay. $1.44. Anybody else get a different answer? Okay. Well, nobody got a different answer. If they did get it, they're not saying. So, all right. So what's the first thing I got to do here? What do I do first?
P equals voltage times current.
Okay. I got to get the power first. I got to get the number of kilowatt hours. Remember, I got to take kilowatt hours times hours. So what he's saying is I can take these two. P equals V times I will give me the power. So I got 120 volts. I got 5 amps of current. My power is 600 watts or 0.6 kilowatts. So that's one thing that I will need. P equals 0.6 kilowatts. And my time, it says we're going to use this for 1 day. That's 24 hours. So now all I got to do is figure out my kilowatt hours. Well, kilowatt hours is just equal to the number of kilowatts times the number of hours we're going to use those kilowatts. And we said that we got 0.6 kilowatts. We're going to use that 0.6 kilowatts for 24 hours. So how many kilowatt hours of energy is that? When you do the math, it's what?
14.4
Okay.
kilowatts per hour.
14.4 kilowatt hours of energy. Remember, that's not power, that's energy. Kilowatt hour is a unit of energy. And then, we're going to multiply that by 0.1 because we're using 10 cents per kilowatt hour. So multiply that by 0.1 to change this from kilowatt hours to dollars. It moves a decimal right there. And that gives me $1.44. Now, is that a lot? Is that a lot? And you may not. Some of you are like 18, 19, you never paid an electric bill. But you think $1.44, is that a lot? Is that a lot of money to pay for cost of energy?
If I'm not paying the bill, then it doesn't seem like it, does it?
Hey, I got a nephew like that. Well, he's not there now, but for the last 3 years, probably last 2 years, he's been using my electric. I've been paying for it, so you're right about that. If you're not paying for it, then it's not a lot. But think about it like this. You don't pay on a per-day basis. You pay basically monthly. Maybe every 30 days you pay your electric bill. And so if you spread it out over 30 days, let's say, think about the clock in problem number, what was it? In problem number 7, you had a clock that was 5 watts. You kept that clock on all day for 30 days, 24 hours a day for 30 days. It only cost you 36 cents for the whole month. So if you divide 36 cents by 30 days, this costs you really fractions of a cent per day. Where this, if you got a calculator, multiply 1.44 times 30. Multiply that times 30 days. How much is that over a 30-day period?
A little over $43.
How much?
$43.20.
So $43.20, which still might not seem like a lot to you guys, but I think I have a 2-bedroom apartment and my heat's covered, it's paid for. I just have my refrigerator is electric. Sometimes I plug in an electric heater. My electric bill might be about, I don't know, 90 to 100, 110, 120 bucks. So I think, if it was like $90, that's like almost half just for that one heater. So to me, even though $1.44 by itself is not a lot, I think for a heater, I think that's a lot of money. $1.44. When the clock was only costing me 36 cents divided by 30 days, whatever that is, I think $1.44 is a lot. But you guys make a lot more money than me, I'm sure. $1.44 is nothing for you. You don't mind paying it. And like, I don't know who that was that made that comment, but if you're a kid at home and your parents are paying it, you don't care anyway, so what the heck? Hey, hey, hold on, guys. I see a student. Hold on. I'm going to leave the mic on so you can hear me say. What's going on? How you doing? I guess we got to do that, but I hate that. I hate you can't shake hands and all of that. Are you doing okay?
Yeah.
You text me your number. I want to talk to you, see how things are going for you.
Oh, really?
Yeah. Can you, what class are you here for?
I'm taking computer repair.
Me too.
Yeah, you told me.
Yeah, but I'm teaching during that time, so I can't be in there.
Oh.
So, okay, good. But what made you take that?
You told me.
Yeah,
Because he's
good.
going to retire, so.
Well, I'm so happy. Good that you listen. Good.
Yeah.
You will never get a call like that again. You will never find a way to teach it like that. So we'll keep in touch. So you'll be here on Tuesday.
Yes.
We'll talk, and I'll get your number later. Then I'll see you. Okay.
Thank you, sir.
Good seeing you, man. Wow, it's good to know that some of you students actually listen. So that was one of my former students, and I'm taking there's a guy here. He's our lab tech. He's retiring after this semester, and he's been here. He teaches PC repair, computer repair, and I swear you will never ever find another person to teach it like he teaches the old school way. I mean, you actually know how to fix the thing. And so he's retiring. I've been saying over the years, I need to take this class. I want to take this class before he retires. Well, I kind of got boxed in because he's retiring after this semester. And the classes are like, there's 3 classes you want to take. So I want to get them all from him. He's going to retire, but he'll come out of retirement to teach the next 2 classes, and then that's it. But this student, if you heard me talking, this kid, I had him maybe last year. I think I had him in class, maybe the year before last. But I told him about real estate investing because I do that when I'm not doing this. I'm a real estate investor. And I told him about taking this class before the guy retired. This guy actually listened. He's a real estate investor. He owns a couple buildings now. And he's taking this class that I'm enrolled in during this time. So what I got to do is when I'm teaching you guys, he records all his videos. I'll record them, and I got to make the labs up. It's a long story, but I'm happy the kid listens. So he's going to be really, really well off here. So anyway, you're not here for this. You want to know about this problem. So $1.44 is correct. Anybody have any questions or comments over this problem?
I just want to say, if you really think about it, you're converting electricity into heat. So $1.44 a day doesn't seem that bad when you think of it that way.
Okay, if you don't want to be cold, I'll let you have that. But I still don't want to pay $1.44. Well, I might, if they took it away from me and as cold as it is, you might be right. You might be right, but I think it's a lot compared to the clock. What do you guys think? I guess we're the only 2 with opinion. Who was that? Who was that I was talking to?
I think it's a bad deal, really. I mean, I feel like you should be able to power everything in your house for a couple $100s. And I'm talking like TVs, everything, you know, your phone being charged. Because I can literally point to like 12 things that are plugged in right now. And if this were the case, you know, like it would be thousands of dollars a month for my power bill, I guess.
Well, guys, on the old, not the new ones, but on the old electric meters, they had an aluminum wheel that turned. And when you guys come in, I might show you an electric. You guys are coming in next week. I got an electric meter I might show you. Where is that electric meter? Yeah, one of my houses, I got an electric meter. It has an aluminum wheel in it that spins around. And the more energy you use, the faster that wheel's going. So if I just had the heater plugged in, it probably wouldn't spin that much. But there are people who actually have solar panels put on their roof. And if you have enough panels on your roof, you can actually produce more energy than you would use. And at that point, your meter literally runs backwards. Your meter will run backwards, and Duke Energy will send you a check. They owe you money. So when you guys get out, get your jobs, make sure you don't get married right away. Wait on that. Have some fun first. Save up some money. Buy a house and put solar panels on it, and get money from Duke Energy. Somebody sent a text. What was it? Oh, I don't have my thing. I can't see it because I'm sharing the file. So if you send me a message, I can't see it. All right. Look, I'm running out of time. Let me stay focused. A couple more things I want to talk about. So take notes on this because there's a lot of pieces to this, and I want you to have it all in one place. So let me, who was this? Somebody said something about charging the phones and laptops. Well, guys, now listen, if you take your laptop and you plug it into the wall, listen, if you take your laptop and plug it into the wall, and then you unplug your laptop, then you plug your cell phone or whatever into your laptop and charge it off the battery. Say you charge your cell phone off the battery in your laptop, you're still paying for that. I mean, it doesn't matter that you're taking the energy, you're still paying for that energy. Because now you got to plug your laptop in again to get more energy, unless you go somewhere else and get energy for your laptop.
Well, my plan is to charge my laptop off my phone, and then they'll just both keep charging each other forever.
Say it again.
Genius.
So
Charge
how
each other.
about plugging in the charger but connected to the laptop is what cost? Sometimes we plug in the wire, but we don't plug in the charging cable to the laptop, so it will cost.
You plug in the cable to the laptop.
Yeah, oh no, I mean like I plug in the adapter of the laptop, but I don't plug in the laptop. so it will cost. Yeah,
I think she's saying like the
yeah.
battery pack, if it's plugged into the wall, but it's not plugged into your laptop, are you still getting charged even
Yeah,
for it to
yeah.
be plugged in?
Yeah. Well, I shouldn't say, yeah, I need to see exactly what you're talking about. But I tell you what, if there's an LED light that lights up on it, or if you put your hand on it and it's warm, then you're being charged for it. It's kind of hard to see without looking at the circuit they have. If you have some kind of mechanism that actually, like a switch actually opens up, so there's no current flowing into it, then you're not being charged. But a lot of times that thing you plug in the wall is called a transformer, and that transformer actually uses power even when you don't have anything plugged into it. So it just depends.
Technically, on the commercial side of things, there is current draw, regardless of whether or not you have anything plugged into it. So even if you just have a bare power strip with nothing on it, you're paying very, very small amounts of money to do that.
Yeah, I know that even if you don't, like if I'll tell you, I have some units, some rental units, and I can have a rental unit, like I got one now that's empty, and I can keep everything turned off. And I still got to pay a minimum charge, but that's just for the meter to be there. So I don't know if it has something to do with what he just described or what. But I have it might be $17 a month or something like that, but there's always a charge, regardless of whether I'm using power or not, or I'm using energy or not. All right, guys, so let's talk about this. So power is a rate of doing work, and it's also a rate of converting energy from one form to another. I can talk about electrical power, which we measure in watts. And then there's mechanical power. So that if I have some kind of machine, like a motor, some kind of machine that moves, then usually they don't rate that in watts. They use something called horsepower. So the unit for this is a capital W. And the unit for this is your lowercase HP or uppercase HP. I like to use the lowercase one. So now it doesn't have to be this way. If you wanted to, you can give mechanical power in watts and electrical power in horsepower. So maybe you got a speaker, 100-watt speaker, you can convert that to horsepower and see how many horsepower speakers are. Or you buy a new Corvette, instead of having a 500 horsepower engine, you're gonna have a 5,000 watt engine. This just doesn't really matter what you use, but just kind of by convention or by agreement, we tend to use watts when we're talking about electrical power and horsepower when we're talking about mechanical power. Now there's one little thing here that I want to make sure you're clear on. When you're talking about electrical power, we're usually talking about the power going into something. And when you're talking about mechanical power, you're talking about the power coming out of something, some machine. So let me show you what I'm saying. Say you have a microwave. Here's your microwave. Here's the cord that plugs into the wall. And on the microwave, there's probably like a sticker that tells you information about the microwave. They might tell you that the voltage is, they might say 120 volts AC. They might say 1,000 watts. Well, that 1,000 watts is the wattage going into that plug right there. Now, wattage doesn't really move, but it's the power flowing into the plug. Whereas over here, I might have a machine like a motor. So I got the motor, here's the body of the motor. Here's the shaft that spins. There's a motor. And here's the shaft that spins around. That spins. And that shaft, I might have a fan blade on there. It might be a pump. I got a motor, and it's spinning, and it's a 7 horsepower motor. Well, if it's a 7 horsepower motor, it's an electric motor. So I got this hooked up to I get voltage, voltage and current connected to the wires over here. If it's a 7 horsepower motor, it's not 7 horsepower going in. It's 7 horsepower available at the shaft, and the shaft is the output. So this is the output power. be 7 horsepower. So if I'm talking electrical power, we're going to use the units of watts, and that would be the power going into the system. If I'm talking about mechanical power, by convention, by agreement, we're going to use horsepower. And if I have a motor rated at a certain number of horsepower, that's going to always be the power available at the output, which in this case is the shaft. The other thing you want to know about these two is the relationship between one and the other, because often you got to convert from electrical to mechanical or vice versa. So if you're making a list, remember I asked you to make a list, put all the equations on there. Also write on there that in this class, we're going to use 10 cents per kilowatt hour for cost of energy. We're going to use 720 hours for 1 month, and a month in this class will always be 30 days. So write all that down. But in addition, I want you to write 1 horsepower is equivalent to 746 watts. 1 horsepower is equivalent to 746 watts. Okay, any question over electrical power, mechanical power relationship, conversion factor, or concepts? Any questions or comments over that? Okay, well, I want to add 2 more words to our list here. Current, separation of charge. I'm getting tired is what it is. When I start making all these mistakes, it's because I'm past my bedtime, which if I wasn't here, probably would have been about a half hour ago, to be honest with you. I start my day at like 4 in the morning. So now I'm getting sleepy. Anyway, voltage is a separation of charge. Current is charge in motion. Resistance, opposition to current flow. Energy, ability to do work. Power, rate of doing work or rate of converting energy from one form to another. I want to add 2 more to this. I want to talk about something called a transducer. I'm going to probably put it up here. I don't know if you guys can, well, you probably can see that. Let me get rid of this. All right, so transducer and efficiency. These are our final 2 terms for tonight. Transducer and efficiency. So let's talk about what do I mean by transducer and what do I mean by that term efficiency.
I'm looking forward to learning about transducer. I've heard that word so many times at work, and I've never really known exactly what it means.
Yeah, transducers are cool, really cool. All right, so let's deal with that transducer. So what is a transducer? Let's define it, and then we'll talk about it. So a transducer, you write it down. I'm not going to write this out. I'm going to say it slowly, and I'll say it a couple times so you can write it down, but I'm just going to put the term on the board. So transducer. The transducer is any device that converts energy from one form to another. A transducer is any device that converts energy from one form to another. So write that down. A transducer, any device that converts energy from one form to another. Now, the conversion process can be, sometimes it can go one way, or sometimes it can go 2 ways. So if the energy conversion process goes one way, we say that the transducer is unidirectional. If it can go both ways, 2 ways, we say it's bidirectional. So what I want to do is, I want to give some examples of transducers, And I'm going to give some specific example of what I mean by unidirectional and bidirectional. So here's some transducers. A light bulb is a transducer. It's a unidirectional transducer because I can put electrical energy into a light bulb and I get light and I get heat out, but there's no way to put light or heat in the light bulb and get electricity out. So it's a transducer because it converts energy from electrical energy to light energy, electrical energy to heat energy, but it's unidirectional. Whereas I can have a motor. A motor, I put in electrical energy and the shaft will spin. So I put in electrical energy, I get out mechanical energy, a motor. But I don't know if you know this or not, but I can take a motor, a basic motor, and I can spin the shaft and get out electricity. So basically a motor and a generator are the same exact thing. If I put in electricity, the shaft will spin. If I spin the shaft, then I get out electricity. And I actually have, if you remind me when you come in next week, I actually have one of those little toy motors that that you hook a battery to, and you probably spin them and then you reverse the battery, they go the other way. You might have played with those as a kid. I have one of those with a handle on it, and we can spin it, and it'll actually light up a light bulb. Or we can take a battery and put on the light bulb output, it'll spin the handle, demonstrating this fact that a motor is a bidirectional transducer.
That's cool.
Let me see more examples. We got a speaker. A speaker is a transducer because we put in what? We put in electrical energy and we get out acoustical energy or sound. It's a transducer. You might not know it's this kind of transducer because you can put electrical energy into a speaker and get out sound. You can also speak into a speaker and it causes electricity to flow into the circuit. So you can use a speaker as a microphone. It's a bidirectional transducer. So a transducer, any device that converts energy from one form to another, and then the energy process, the conversion process, can either go one way, in the case of a light bulb, or it can go two ways, like a motor. Put energy into a light bulb, I can only get light and heat out. There's no way I can put light and heat back into the light bulb and get electricity out. With the motor, I can. I can put electricity in, I can get mechanical energy out. If I put in mechanical energy, I get electricity out. So I got those two energy conversion process. Now, let's talk about a general transducer. It could be anything. It could be a motor, a speaker, whatever you want it to be. I'm just going to call it a transducer. So let's say I have a transducer. Here's the input. Here's the output. So what happens, I'm going to get energy flowing into this. And I'll get energy, this will convert it. So there's some kind of converting here. This will convert the energy. I'll get some other kind of energy coming out. So the energy going in, I'm going to call that E in. And the energy coming out, I'll call that E out. Now, what I like to happen is this. I would like for E out to equal E in. Why would I want that relationship? If I had that relationship, what would that mean? If I had E in and E out equal together?
It'd mean that you had 100% efficiency.
Yeah, that's the word. It means I have 100% efficiency. That means that all the energy I put in is being converted to useful work. And that's what we strive for. We want things to be 100% efficient. And so here's what they do to calculate efficiency. Well, they have a symbol for efficiency. You might think it's an E, but they don't use an E in electrical engineering because they use that for voltage and electric field. So they use this funny looking N. represents efficiency. And that's actually not an N, it's the Greek letter eta, or eta, ETA, it's the Greek letter. And to calculate efficiency, it's really simple. Efficiency equals energy out over energy in. And you can see if E out and E in are the same, then this quantity right here would equal 1. They're the same number. Now what happens is when they calculate this, sometimes they'll multiply this by 100%, and they'll look at efficiency as a percentage. So that's why, I don't know who answered the question, but he was like, it'll be 100% efficiency. 100%, I'm so tired. It will be 100% efficient. So often we talk about efficiency in terms of percentages. It's silly to use the word efficiency away from, when you talk about the efficiency, it's always the efficiency of something. And the something we're talking about is a transducer. So when you use the word efficiency, you're implying that there's some kind of transducer. You just got to think about what you're talking about. Now, will you ever get 1 for efficiency or 100% efficient? The answer is no. It's impossible to get 100% efficient or efficiency of 1. So what we strive for is to get as close to 1 as I can. Now, what happens in this system, energy flows into the system, energy flows out of the system, but there's always going to be energy, actually I'm making it green. It's always going to be energy loss. In any transducer is going to be energy loss. Like a motor. A motor is a transducer. You have electrical energy going in, electricity going in, the shaft is turning, so you have mechanical energy coming out. But if you put your hand on the motor, if it's an electric motor, it feels warm. The reason it feels warm is because there's resistance in the motor, and in overcoming that resistance, you're using some of the energy to heat the motor up that would have otherwise been going over here. So if you feel heat, and you will feel heat, that means you're not getting 100% of the energy out. Some of it's going to heat the motor. If you can hear the motor running, what is sound? Sound is vibrational energy. That means the motor is vibrating, which causes the air molecules to vibrate, which causes your eardrums to vibrate, and you interpret that as sound. But the fact that the motor is vibrating means some of the energy going in that you want to turn the shaft, some of that energy is going to vibrate the case of the motor. So there's a whole bunch of little tick-for-tack things that you can just lump together and call it energy loss. So there's never, ever, ever will you have this. What you will have is this. You'll have energy going in equal to energy flowing out plus whatever your loss is. So if you're designing a transducer, what you want to do, you want to make this as small as possible. Because if this is smaller, that means more of this is going to that, and less of this is going to that. But there's one more term here. Sometimes, depending on the transducer, sometimes you actually have energy stored inside the transducer. So let's say you have a mechanical transducer that has a spring in it. If you compress that spring with some of the energy going in, and that spring stays compressed, then that spring has potential energy that came from E in. And it's going to stay there until you decompress the spring. Or if you have a device, a transducer, now you guys probably don't know what a capacitor is, but you will. We'll talk about capacitors at the end of the semester. A capacitor is a little electrical device that it'll store charge, it'll store energy, electrical energy. Many machines or devices have capacitors in them. So if you have a transducer that has a capacitor in it, when the electrical energy flows in, some of that energy goes into the capacitor and it's held there, and the rest goes out to the output. So that's stored energy. No matter what, often you have transducers that you're going to always have energy loss, and sometimes you're going to have energy stored. So this equation, even I have to add that other term to it, E stored. So the idea is you want this and this term to be as small as possible. Okay, but to describe the whole system, you need all these terms. E out, plus E lost plus whatever stored equals what goes in. Basically, that's a statement of the conservation of energy principle, which means energy can't be created or destroyed. You have to be able to account for all the energy going in and out of the system. Now, let's talk about some efficiencies. So, the average car engine, now this number is old. It might be better now. I don't know how old, probably maybe 10 years old. But the average car engine is about 30% efficient. The average car engine is about 30% efficient. And it depends on whose website you look at, but it's around 30% efficient. What does it mean to say that? If I say that this engine is 30% efficient, what does that mean? What does it mean?
The energy put into it is only, it's 70% less than what it actually outputs.
Okay? The energy flowing into it is 70% less than what you put into it. So if I put in, I don't even know how to say it, but here's another way to I'm going to turn what he said around. That means only 30% of your energy, 30% of your energy comes out as useful work. Well, a car engine is a transducer. You put in you put in petrochemical, you have potential energy stored in the gas lane, it explodes, it comes out, and it changes that to rotational energy of your tires. So 70%, if I say the engine is 30% efficient, you can also say it's 70% inefficient. 70% of the energy you put in is flushed down the toilet. 70% of the energy you put in goes to something else other than turning your wheels. Only 30% of that energy actually goes to do what an engine is supposed to do, to turn your wheels. Now in the car, most of the energy used is used in overcoming friction. So 70% of the engine, 70% of the energy is used, but the engine gets hot, so that's wasted energy, the heat. Although sometimes we use that heat. When you turn your car heater on, you're using heat off the engine. But for the most part, heat is an energy loss. It will be here. You hear the engine running, that's an energy loss, vibrational energy. Only 30% of the energy goes in to turn the wheels. So that's a combustion engine. Now, electrical motors, you have an electric driven car, those are way more efficient. I can make a electric motor way more efficient than the combustion engine. Matter of fact, I heard an announcement today that by 2035, General Motors is saying they're going to replace all their gasoline engines with electric. And that's like 2035 to a car company is like tomorrow. They plan out decades. So that's a big thing that they're saying. Don't do it now, but after class, you might want to Google that. By 2035, and I think everybody has their eyes on Tesla. Tesla has done a hell of a job with their electric vehicle fleet. They've done, I remember when there was just an idea, people wouldn't bet on Tesla, but Tesla's done very, very well. So Ford already has a bunch of electric vehicles coming out. They might already be out. They have an electric Mustang that I saw a commercial for. And GM made the announcement, I heard it today, that by 2035, they're going to replace their whole fleet with electric vehicles. So now here's the most inefficient device ever created by man, is an incandescent light bulb. So you got, right now we have incandescent, that's the old light bulb with the filament. You screw them in and they get really hot. Then there's the lights in here, they're the long tubes. That's a fluorescent bulb. And then you have incandescent bulbs. So you have incandescent, fluorescent, and LED. Well, the incandescent one is the old school bulbs. And those are only 5% efficient. 95% of the energy put into an incandescent bulb is wasted as heat. Those things are so inefficient, they should be outlawed. They're so inefficient that when I was a kid, I'm not going to tell you how old I am. It was a long time ago. When I was a kid, my sister had a toy. It was called an Easy Bake Oven. And you can actually take a light bulb, and she would put the light bulb in the oven, and you could bake cookies and cakes with a light bulb, because a light bulb is a better heater than the lighter if you're talking about an incandescent bulb. They're very inefficient. the fluorescent bulbs are about 25% efficient. If you notice, you can take say you take a 60-watt fluorescent bulb and a 60-watt incandescent bulb. You can put your hand on a 60-watt fluorescent bulb. It feels warm, but you can keep your hand on it. If you put your hand on a 60-watt incandescent bulb and put it there, you'll get burned. You'll eventually have to take it off. You also notice that the fluorescent bulb, 60-watt fluorescent bulb, burns brighter than a 60-watt incandescent bulb, because with the fluorescent, more of the energy is going into light, and with the incandescent, more of that energy is going into heat. Really, wattage is a terrible way to, when they talk about brightness, wattage is not a good way to do it because you don't know the efficiency of the device. A better way to do it, to talk about brightness in physics, they call luminous intensity. And the unit is called a lumen, and that lumen is based on brightness of a candle. You can look it up yourself, but wattage is not a good way to determine brightness of a bulb, although that's the way we do it. What else? I think that's it for some examples, but we got to calculate efficiency, guys, but here's the problem. Let me show you this. To calculate efficiency is the ratio of the energy out to the energy in, and what you'll find is that E out is always less than E in. You'll never have a case where they're equal or where the sign is the other way. But how do I get this ratio when all I know is voltage, current, resistance, or power? How do I get it? Well, let me show you something. Let's say I did this. Let's say I took the ratio of P out to P in. Let's play around with that and see if we can make this look like that. Well, you already know that power is energy per unit time. It's in joules per second. So that means that this right here is energy per unit time. And this right here is energy per unit time. It should make sense to you that if I'm talking about the power out, and I'm talking about the energy out per unit time, I'm talking about the power in, I'm talking about the energy in per unit time. So really, in taking P out divided by P in, what I'm doing is taking energy out over T, because that's the formula for P out. And for P in, I'm taking energy in over T, because that's the formula for P in, and I'm dividing those. So let's divide it out and see what happens. If I take the numerator, which is E out over T, and I divide that by the denominator, which is E in over T. If I actually do the math, and remember, when we divide fractions, what I do is I take the first fraction, leave it as it is. I change this to multiplication, then I gotta flip that over. And if you multiply that, you see what happens to the T's? You end up with E out over E in. So what that's saying is, by taking the ratio of P out over P in, I actually get E out over E in, which is that. So what that means is, yeah, in physics, we talk about efficiency, we like to do E out over E in because that's what physicists do. But electrical engineers don't deal with energy directly. They usually deal with voltage, current, resistance, power. But you get the same number by taking P out over P in. So even though in physics it's defined this way, we're going to do it the engineering way. We're not going to use this one. We're going to define efficiency as P out over P in. So you go ahead and add that to your equation list. And this will be our mathematical definition of efficiency. Okay? Any questions over the concept of Any questions over transducers or the concept of efficiency or any of the formulas or derivations I've done tonight? Any questions or comments?
I just wanted to say that I was curious and did a quick Google, and apparently halogens are even less efficient than incandescent bulbs.
Really? What's the efficiency of a halogen?
It says between 2 and 3.5%.
You got to be kidding me. Are you serious? My mind is just blown right now. And you know what? I'm rehabbing. This is crazy. I'm rehabbing a house right now. I'm rehabbing a house, and I just redid the bathroom. And I'm looking for a vanity light, and the one I was gonna buy was a halogen. And the only reason I didn't want to buy it is because I can get an LED light that'll last for 10 years. I don't have to worry about it. But the halogen looks so good. It was just a really nice light. But at 2 to 3%, there's no way in the world I would buy that, even though I'm not paying the electric bill. That's
I had a
interesting.
halogen in my old apartment, and it got so hot it warped the countertop.
Isn't that crazy?
Yeah, just shining down all the time. But it was
So
good for
that
drying my dishes.
right. So there you go. So that's an example of how much energy is wasted. Well, they ought to be outlawed too, then, right along with incandescents. Now, I don't know the efficiency of an LED. They're pretty high compared to the other ones. So you guys might want to look that up. Okay, well, it's getting late. We got 2 more problems to do. We got 2 problems, and I have one more thing to talk about. And I said we're going to be 9 o'clock, but I got off on the side conversation. So sorry about that. Let me put the sheet up. I want you to work the next 2 problems. I have one more thing to tell you tonight, one more topic, a brief topic related to this I want to talk about, and then we'll call it the night. So I'm going to share the sheet with you. We have to do problem number 9 and 10. Go ahead and try number 9, and then we'll talk about it, and then 10, and we'll talk about it, and I'll wrap up the lecture, and then we'll get out of here. So I've still got 14 people. I appreciate you guys hanging in there with me. So go ahead and do problem number 9. I'll give you a few minutes to do problem number 9, and then we'll talk about it, and then we'll do 10, and I'll get the last closing comments, and then that'll be it. Problem number 9. Okay, guys, I'm gonna give you 2 more minutes on this problem, and then we'll take a look at it. 2 minutes. All right. So, problem number 9. You have a 4 horsepower motor. It draws 20 amps from a 220 volt power line. They want to know the efficiency of the motor. They want to know how much it will cost to use the motor for 12 hours. So what I did, I drew a picture of the problem the way I think about it. Your picture might look different if you have a picture at all. You do want to get used to using you should have a straight edge, a ruler. Get used to drawing pictures when you can, and try to represent quantities that you know and what you're looking for, and it'll help you solve problems. So the first thing we want to do here is I have a mismatch. I have basically electrical energy coming in and mechanical energy on the outside. I got to either have all horsepowers or all watts. So it makes sense I'll need to calculate P in and P out, but I want both of those to be in the same units, and we're going to change them over to watts. So P in is pretty easy. It's going to be V in times I in, and they give us those values. V in is 220 volts, and the current flowing in is 20 amps. I don't have a calculator. Can somebody do 220 times 20? Is that 4,400? I think that's 44.
Yeah, you didn't even need a calculator.
Yeah, for that one. I'm so tired though. I don't know what I need a calculator for and what I don't. Now P out, I got to take 4 horsepower. I got to convert that to watts, but I know that 1 horsepower is the same as 746 watts. So I talked about conversion factors. Well, here you go. Here's one. Horsepower cancels out. So what is 4 times 746? How much is that?
3,064.
All right. So with that, efficiency is simple. Then we can get that real quick. Efficiency is P out over P in. So I
Got
got
it wrong.
what?
It's 2984.
This one?
Yeah, I tried doing it by hand, and I guess I screwed up somewhere.
All right. You said 2984? 2984 watts. Now notice that when I put in the 2984 watts divided by 4,400 watts. Notice the unit drops out. Efficiency is just a number. In engineering, they have these unitless quantities it's called a figure of merit. So one figure of merit is efficiency. It doesn't have units, and a figure of merit means you use that number to compare to other things. Like I might have two transducers. One is 30% efficient, the other is 60% efficient. That means the second one is twice as efficient as the first. So a figure of merit in engineering, it doesn't have units. You just use it to compare things, quantities, devices, or whatever. So what is this? If you take 2984 divided by 4400, how much is that?
0.678.
Is that what you said? 0.678?
Yes, correct.
All right. So it's going to be 67.8% efficient. What does that mean? When I say that motor is about 68% efficient, what am I saying?
About 2/3 the energy you put in actually comes out as work on the other side.
Exactly. About 2/3 of the energy I put in comes out as useful work. The other 1/3 is wasted as heat, vibrational energy, sound, sparking in the motor. All that's a form of waste because we don't want any of that kind of energy on the output. So about 2/3 comes out as what I want, and I want mechanical energy.
They should probably get a new motor.
Okay. But 68% is a lot better than the 30% of a combustion engine. I'm sure this is probably better than 68. Now let's do the cost. Now for cost, which one of these powers do I use? For cost, I gotta get power times hours. I gotta get kilowatt hours. But in getting kilowatt hours, do I use the 4400 or do I use the 2984? Which one do I use? Which one does it make sense to use?
4400.
The 4400. You always use the input power. So my power is always the input power is 4.4 kilowatts, and the time is going to be 12 hours. So we got to get kilowatt hours of energy. So what is 4.4 times 12? How much is that?
52.8 kilowatt hour.
How much?
52.8.
All right, so that's going to be $5.28 to run that motor for 12 hours. Okay? All right. Well, we got one more problem and one more short concept, and then we're done. I'm going to give you a couple minutes for the problem, and I'm going to need about 3 minutes for the concept, and then we'll be done. So let me switch back over. Does anybody have any questions over anything I did on this problem before I do that? I'm not trying to rush. If anybody has any questions, I'll be happy to talk about it. Anybody have any questions or comment? Okay, well, let me share the document. We'll do the last problem. I got one more thing I want to share with you, and then we will call it a night. So here is, and I also want to show you the energy project before you sign off. So here is the last problem, practice problem number 10. See what you can do with that. Give you a couple minutes, and then we'll talk about it. Okay, guys, I'll give you about 60 more seconds and then we want to talk about the problem. Problem number 10. This is our final problem of the night. It says you have a 5 horsepower motor and that's 80% efficient. I want you to calculate the current draw from a 220 volt power line or power source. So here is my picture. I listed efficiency. They gave us efficiency of 80%. All we know is the efficiency, mechanical power, and the voltage, and they want us to figure out the current. So when I looked at this problem, I immediately thought of, if they gave us this, they must want us to use this equation. The fact that efficiency equals P out over P in. And that makes sense because we know this, and P out I can get from converting this over to watts. The only unknown here is the input power. So let's go ahead and do that. Let's convert this over to watts. And let's fill in this equation with what we know and see if we can figure out what we're looking for. So P out, to get the output electrical power, I got to take the mechanical power and convert that to watts by taking 5 times 746. So anybody do that conversion?
It was 3,730 watts.
All right. So we know that this number is 3730. And we know that this is 80%. So we know that this, if I change that to a decimal, it's 0.8. The only thing we don't know is the input power, but if you think about it, we don't really need it. What we really need is what it's equal to. Pn is equal to V times I, and what we actually want is this. So I know this is 220, and if I knew I, Pn would equal 220 times I. If I knew I can get Pn, but we're not concerned about that. We really only want that I. So I'm just gonna, instead of putting this down here, I want to put what this is equal to. I want to substitute this for what it's equal to, V times I. And I know V is 220. So if I do that, the only unknown I have here is I. And if I solve this for I get 3,730 divided by 220 times 0.8. I don't know how much that is. Somebody has a calculator. Make sure you use your parentheses on that.
21.1 ampere.
21.1?
Ampere.
All right. All right, so there you go. So that was more of a math problem than anything. It's not a whole lot of engineering in that one. It's just a math problem. So, any questions on this problem? Any comments? Okay, I got one more thing I want to share with you. Just take a few minutes. and then we'll call it a night. So the last thing I want to talk about, often when you have, you're dealing with efficiency and transducers, often you have more than one transducer, and they're usually hooked up a certain way. And we say that they're a cascaded system. So I want to talk about efficiency, cascaded systems. So what is a cascaded system? Well, a cascaded system is when you have more than one transducer. The input of one transducer comes from the output of another transducer. So it's like this. You got this transducer, and that's connected to another transducer, and that's connected to, and I can have as many of these as I want until I get down here to the last transducer. See over here is where my energy comes in, and the output of this is the input of that. And the output of this is the input of all the way to the last one. But here's my final output over here. So this is a cascaded system. So an example of this will be, let's say you have, now Duke Energy, I think we produce our electricity using steam. They burn coal and they boil water and they shoot steam up to some turbines. But in other places, they have they'll dam up like a lake, and the water falling over the dam would turn turbines. So you might have turbines here. The water falls down. This is a turbine. Well, that's a transducer. It turns the potential energy of the water. It rotates. It turns that to mechanical energy, which the turbine might connect to a generator. So that's another transducer. And then the generator might actually power a motor. That's another transducer. And the motor might do some work over here. This is what you want. So you go through all of these transducers. That's a cascaded system. Another cascade, your car is a cascaded system. You have your motor, which is a transducer, but then the motor goes to the transmission, which is a transducer. The transmission goes to the differential, which is a transducer, and then it spins the wheel. So often you have more than one transducer hooked up. So how do you deal with efficiencies of cascaded systems? And it can be as easy or as detailed as you want. I can look at the whole system. So if I put this in the box, if I put this whole thing in a box, and let's say I couldn't see all the subsystems, all these individual transducers. All I see is energy going in and energy going out. I can still get the overall efficiency. I'll call it the total. By taking that E out and E in, and I can divide those, get the efficiency of the whole system. But it turns out, let's say that this transducer is efficiency 1, this is efficiency 2, 3, 4, 5. This is efficiency N. That's the last one. I'm using that N. I can have any number of efficiencies. If you look at it that way, then I can also get the total efficiency by multiplying the individual efficiencies if I have these cascaded transducers. So what I'm saying, the total here would be the first efficiency times the second efficiency times however many I have, all the way out to the last one. So there's two ways I can get efficiency of a cascaded system. I can take the total E in, total E out, and divide it. I can use E total equals E out over E in. If I know the energy, total energy coming in and the total coming out, I can get to it that way. But now I can get a little bit more information with this one. Now, this is important because let's say that the job you have to do is you have this cascaded system of transducers, but you want to increase the efficiency. What do? Well, let's say we have, let me show you. Let's say we have 3 transducers cascaded. Let's do that. 3 transducers cascaded. So I have this transducer feeding this one, feeding this one. So here's my E out, and here's my E in. And let's say the efficiency of this is 0.79. Let's say the efficiency of this is 0.25. Let's say the efficiency of this is let's say it's 9. So that's really high efficiency. So I want to use this equation to figure out my overall efficiency. So let's do that. So get your calculator. Let's use this equation to figure out my overall efficiency. So my total efficiency would be 0.79 times 0.25 times 0.9. What would my total be?
0.177.
All right, I just rounded. You see what's going on here? When you multiply decimal numbers, then the product is always less than the smallest number. So my product had to be less than 0.25. My overall efficiency is 0.18, 18%. And the lowest one, this is really high. That's 79%. That's 90%. But the overall is way down at 18% because of this right here. And that'll always be the case. This would be like the weakest link in the chain, right? So if your job was to increase the efficiency of some cascaded system, you probably don't want to spend much time here or here. This is what's pulling you way down from 80%, 79 there, 90. This is way below 18 because of that. So if you're being paid, you probably want to focus on, hey, what can I do to this transducer to get its efficiency up? And that'll greatly bring up your system if you can deal with that one. These two, you won't get much closer to 100. But this one, you might be able to do something to greatly raise that up closer to the 79 or the 90%. So I don't know if I'll give you a problem with cascaded systems or not, because we're not going to spend a lot of time talking about it, but I at least wanted to touch on it. It is interesting, and you guys are welcome to dig deeper into this. This is some very practical stuff. A lot of things we talk about are not going to make sense until you get later on into your degree program. But chapter 4 in your book, which deals with power and energy, those are pretty they're applicable right now. You can actually understand and do stuff with that like right away. So, guys, I went I don't know. The class isn't over till 10:20, but I didn't mean to talk this long. But thank you for sticking in there with me. Anybody have any questions or comments before I sign off?
So could you, how about energy project?
Oh, yeah. So the energy project I have on Blackboard, I'm glad you said that. And let me show it to you real quick. So here it is. Now, what you're going to do is you're going to find your electric meter in your house, apartment, wherever you live, job, I don't care. I just want you to look at an electric meter. Okay, so what you'll do is you'll write down the number on the electric meter. How many kilowatt hours is that electric meter showing? Now, the point of that is I just want you to, if you never really looked at an electric meter, I want you to look at one to see what it looks like, how it works. Then I want you to find the cost of energy in Cincinnati or wherever you live. So if you live in Cincinnati, find the cost of energy Duke Energy charges you. If you live in Indiana or somewhere else, it doesn't have to be Cincinnati. Just find the cost of energy wherever you live. And then number 3 is where you get into the actual work. You're going to count the number of light bulbs, just the light bulbs in your house. You make a list of all the light bulbs and their wattages. You make the list right in this area. And what you're going to do is you're going to add up all those light bulbs and convert them to kilowatts. And then you're going to answer number 4. Number 4 says, using your list from problem 3, you got the list of light bulbs and the total kilowatt hours. And the cost of energy for problem 2, you looked up how much it's costing per kilowatt hour in your area. They want you to determine how much it would cost if you kept all those bulbs on in your house 24 hours a day for 30 days. How much would it cost you to burn all those lights if you kept them on all day for 1 month? So calculate that. And then number 5, you're going to have to think about. Once you do number 4, they want you to show how would you calculate the total number of electrons going into your house over a 30-day period. How would you do that? So you got to think about that. It's nothing you can just do right away. You got to really, you know enough to do it. Information from tonight and the lecture from last week, you know enough to do it, but you just got to pull some things together, relate some things to see how to actually calculate that. So that's going to count as 1 quiz grade. And what I'm going to do, guys, I'm going to, you'll just bring all this into me next week. You can bring homework 1. You can bring anything. I don't have a link to upload to Blackboard. You'll just bring that into me. And what I'll do is I'll make a list of what's due, what I'm expecting to get from you next week. Okay? So there is the energy project. Thank you for reminding me to show that. Does anybody else have any questions or comments before we sign off?
For the light bulbs include all the basements and garage.
Yeah.
Okay.
You got to bring in I won't let you in if you don't have a face mask. You got to have a mask and you'll be socially distanced and all. We got 2 rooms to spread out, so we'll keep everybody safe. Okay. Well, guys, have a great rest of the night. I'm down 10 people, so, boy, you guys really hung in there with me. So I appreciate that. Stay safe. If you need anything, send me a text, or you can send me an email, but I'll see the text first. And other than that, I will see you guys on, next Tuesday.
So could you please provide the roll numbers and
Yeah, I'll send that out.
yeah.